What's going on, guys? In this free Cloud SOC course, we're going to strip away the buzzwords and focus on how things really work in production cloud environments. You will learn how hackers leave traces in cloud logs, how SOC analysts think when investigating incidents, and how to turn raw data from services like CloudTrail, Azure Activity Logs, IAM logs, and network telemetry into clear security decisions. This course is built for practical learners, no theory and no fluff. We will also do realistic scenarios, labs, and go through common mistakes and the exact mindset SOC analysts use when responding to suspicious behavior in the cloud. Before I start, it's very important, guys, to check the description of this video so that you can have a look at the references used to create this course. Very important. In this video, we're going to talk about cloud investigations and the difference with or between cloud investigations and endpoint investigations. You see, because the SOC landscape changed, endpoints, I understand they are still critical, but today's real battlefield is the identity plane. Let's break it down. So as a SOC analyst, of course, you know, in endpoint investigations, for decades, you lived in a world where you focus on processes, binaries, registry changes, file modifications, as you can see, network traffic, malware behavior, memory forensics. You actually follow the host, right? Your workflow looks like this. For example, you follow a suspicious executable. You find that it spawns a PowerShell, and the PowerShell in turn downloads a payload. The payload adds persistence, and then later on it contacts or it communicates with C2 servers. You see, and then it's a device-centric model. You always start with what did malware do on this machine? And based on experience, of course, I assume, guys, you know that your artifacts would look like EDR detections, Sysmon event IDs, Windows event logs, Linux edit logs, memory dumps, volatile memory. You know the drill. Endpoint work is tactile. You can touch processes, inspect files, you can even kill tasks and isolate machines. However, you will see that cloud changed everything. You will see in the cloud investigations that there is no registry, there is no file system to inspect. Yeah, I know sometimes you will have to do some round of investigations on VM instances. However, in the cloud, everything is an API call. So typically what you will investigate in a cloud environment, you will investigate identities, which is the most important. Remember this, identities first, then tokens, roles, permissions, and trust relationships between these identities and API calls. Of course, you will go over automation, the workload identities, and of course, don't forget the compute instances or the ephemeral compute. All right, now let's talk about cloud artifacts. Usually cloud artifacts are behavioral. You don't investigate cloud artifacts based on files. It's based on behaviors. For example, why this role was assumed, admin, manager, why that Lambda function executed unexpectedly. Okay, these are typical behavioral artifacts, right? That's how you will do your investigation. In this module, we're sharpening the mindset that defines a world-class cloud SOC investigator. Because let's be clear here, cloud investigations are no longer, glorified log searches, and that brings me to the mindset shift number one. You do not ask what happened. You should ask, what was the hacker trying to accomplish? Examples. Attackers usually try to do identity escalations, persistence through automation. They also try to create shadow admins, and also data staging. Cloud logs are actually just the breadcrumbs. Your job here is to reconstruct the hacker's strategy. That's your first mindset. The mindset number two is you should do or get used to what's called as the offense-informed defense. A 2026 analyst knows cloud MITRE mappings instinctively. For every tactic and technique, you should map them to the specific log scenario. For example, in credential access, it maps to get secret value, decrypt, list access keys. Another example is privilege escalation maps to attach user policy, create policy version, pass role. That's what you should hunt for in the logs. Okay, you should map them to the relevant MITRE tactics and techniques. So at the end, you do not wait for an alert. What you're doing, you are predicting what is the next malicious API call should be. The number three Now that brings me to mindset shift number four. Everything as a code equal everything as evidence. Modern cloud attacks often begin before deployment. A cloud investigator or a SOC cloud investigator usually should check for example, Terraform misconfigurations, GitHub actions on secret logs, the CI/CD tokens and API invocations from automation pipelines. If you're not investigating the pipeline, you're investigating half the story. And mindset shift number 5, analysts do not search logs anymore. We actually interrogate the entire system. For example, a SOC investigator should interrogate every identity, every role, every secret, and every bucket in your cloud environment. Also, an investigator should reconstruct timelines and identify deviations from expected cloud behavior. Another thing of interest is the API events with the metadata resources attached to them. And of course, an investigator should correlate logs across containers, serverless, and data layers. You see, at the end, you're not reading logs here. You're running a full forensic review of your cloud environment. In the next section, I will give you guys a quick look on the available cloud shells in the most popular cloud platforms, which are Google Cloud, Azure CLI, and AWS CLI. All right, and now we're going to start with AWS CLI, a quick overview on how to use it. So basically, you can spawn AWS CLI from this button, the Cloud Shell, and from here you can start typing commands. Let me make this a little bit bigger, medium font. Yep. Okay, so let's go back to the notes, and from here, let's first understand the syntax of an AWS CLI command. So first it starts with the keyword AWS, like Google or Azure, followed by service name that we are investigating and the operation we are intending to perform on the service. -- flags if there are any additional parameters we want to supply to the command. In SOC investigations, always we start with AWS with the investigation of identity and access management policies. First, we start with listing the existing users. This will give us an idea if there is any strange or irregular users in our environment. So here the commands, we see AWS IAM. I think it's still small, right? Let's make it larger. Yep. So AWS, here the service is IAM, and the operation or the verb is list users. Here I'm expecting no users because I have not created a user. This is a fresh account. So basically, there is only one user, which is the root user. So the next command here allows us to check the assumptions or the roles on the user. And here we can use the STS service, followed by the operation is get :identity. Here I will be able to see the root user that I have created, which is the only existing users in this cloud environment. You see here, this is the ARN of the account. You see it signals that this is the root account. Using these two commands, you will be able to spot if there is any suspicious users in your Azure cloud environment. Now, of tremendous importance, you can check this also in your node file. This one. Here we are checking if the escalation policy is added to one of the users. See, we use AWS, the service is IAM, and then get user policy, like get :identity. Here we retrieve the policy attached to the username. Here, -- username is the flag we talked about earlier. Username is specified here, and -- policy name is the policy we're looking for if we suspect is attached to the user. Here it's escalation policy. This indicates that this user has escalation or has escalated privileges on the AWS environment. That's a very, very quick overview on investigating users in AWS CLI. Of course, we're going to explain more in the practical labs. The next important aspect of the cloud environment is the buckets, as we explained and illustrated in the Google Cloud CLI activity. So here, first thing we want to do here is to list all the available buckets we have. We want to spot if there is any strange bucket. So list the buckets. As you can see, we have only one. The name is Motasem SOC 01. That's the creation date, and that's the ARN of the bucket. This is also important when you want to reference the bucket name in your investigation, or even when when analyzing CloudTrail logs. Now, the thing is, more important than listing the buckets, we want to find out if there is any strange files inside this bucket. Why? Because when you see suspicious files or unknown files in a bucket, this indicates that this bucket has been compromised and someone, like an attacker, has uploaded data to this bucket, right? Maybe later to perform encryption or to do some exfiltration. How do you investigate the contents of the buckets? Of course, you can use the GUI, but the GUI is actually pretty straightforward. We want to get used to using the CLI. So use AWS, and here the same like the first command, we use the S3 bucket API, and the operation is listing the objects. Now, listing objects requires us to specify the bucket name. That's why the flag here is -- bucket. And here we put the bucket name. So we're gonna copy this and have a look at the bucket I created. The bucket name can be found here. You will see that my bucket is empty. Okay. However, this command will allow you to view all the contents of the buckets. Another important command you want to take a note for is checking the access control list of the bucket. Here we want to find out if the bucket has been exposed to the public. Usually, the buckets that you create, most of the time, unless they serve customers in your project, they are actually restricted to the internal use. So we do not expect any bucket to have permissions or to have public access assigned. Okay. So basically, how do we know that? We can use this command. We call the get bucket ACL operation on the bucket we want to investigate. In addition to the permissions, we also can check the assigned permissions. In addition to access control list, we can check the assigned permissions to those who have access to the bucket. So we can reference the bucket name and see who has access to this bucket and what are their permissions. As you can see, we have one user, okay, and the user ID is this. That's the type of the user, and that's their permission, full control. That's actually suspicious. However, since we only have one user, okay, which is my user, I know I created this bucket, it's actually natural to have the full control on my bucket. However, you should strictly review the output of this command and look for full control or public access assigned with the bucket. This indicates that someone may have compromised the bucket or it's a mistake by your admin. And so always in the cloud, we investigate the buckets, we investigate the IAM, and what else? The instances. Exactly. We check the instances. So much like Google Cloud, what we did in Google Cloud, you can investigate the instances using these commands. These are three basic commands that you can adopt when starting any investigation. Of course, we can explore more commands in the upcoming videos. However, you can practice these commands in your own spare time. And that was a quick overview on AWS CLI. All right, now let's start using the Azure CLI to understand how Azure CLI works. And of course, the basic commands that you need to get familiar with in order to start investigating incidents in Azure environment. Okay, so what you have to do is to access your Azure environment and spawn the Cloud Shell. If you do not have an Azure environment or if you do not have an account, remember that you can subscribe to Cyberdefender, have a Cyberdefender subscription, and then spawn Azure environment. So basically here, that's what I am doing. If you are subscribed to Cyberdefenders, you can spawn this lab to follow through with the commands that we're going to use. So let's start first with the basics. So basically in Azure CLI, all the commands that we execute start with AZ. Okay. And then followed by the noun, which is resource, and the action we want to take on the resource. Dash flags if there are any flags we want to include. So the formula is AZ, Azure, the resource we are investigating, and the action we are taking on this resource. For example, we can list the users with this basic command, Azure, okay, AD user list. That's the action, okay, and then that's the resource. Let's have a look at this command. Check signed in user activity and apply it in the Azure CLI. So AZ starts with AZ, AD signed in user. That's the resource, and then show. That's the action. Here we show the signed in user activity or signed in user identity. So we paste this here. I'll have a look at the output. So as you can see, guys, there is one user which is signed in. It's actually my username, and that's the user principal. That is the username that is signed in. And other basic information such as the mobile phone, the office location, these information are filled by the administrator or the user when they set up their account for the first time. Okay, so that's basic command to see the signed in users in your Azure environment. We can also list the current users in our Azure environment by using this command, Azure AD, or Active Directory user list. Let's have a look. Insufficient privileges to complete the operation. And that's expected because I'm not the administrator of this Azure environment. If you are the administrator, you'll be able to list all the users registered on your account. So for now, you are able to see the users and you're able to see the users who are signed in. Next, let's move on to investigating the roles and the assignments. Remember that after identities are investigated, we want to investigate the roles and the permissions. So here with this command, AZ, role assignment list, we can list all the roles assigned in our AD environment or Azure AD environment. So here, this means that we do not have an existing roles assigned in the Azure AD environment. And that's expected because here I'm using a demo lab environment. Okay, in a fully functioning Azure cloud environment, you'll see a lot of roles. The next thing you want to do, if you want to check who has a specific role assignment, you can use this command. So here we use the same command, AZ role assignment list. However, we specify the role we're looking to audit, -- role followed by the role name. Here we're investigating who has the owner role assigned. Now, why I'm focusing a lot on identities and role assignments, as I said earlier, guys, because most cloud breaches start with the identities and their assignments. That's why I'm only narrowing down the focus when discussing Azure CLI to these commands. Of course, there are a lot of commands in Azure CLI, and this course is not how to teach you how to work with Azure commands, okay? This course is to zero or to zoom in on the commands that you need when investigating cloud incidents. Of course, in the practical scenario, you will have a look at how we work on this using scenarios that include breaches. Okay, so back to the command here with investigating the role assignments where the owner is assigned here. So if you want to take a look at the available roles in your cloud environment, all you have to do is to get back here and execute this command as a role definition list. This will list all the available roles in your Azure cloud environment. And then if you want to extract those with owner label, you can do so either with this command, or you can use this command and then you can use the grep owner. And he will see what are the available roles where owner is matched or spotted. So let's wait and take a look. So these are all the roles where it has owner permissions. For example, this one, cognitive services, Lewis owner, language owner. These are not actively assigned in my Azure environment. These are the roles available for you to assign to accounts and services. Okay. However, when you assign in your environment roles with owner, you can then come back and execute this command and find out what are the identities that have owner as an assigned role. Let's start, or now let's go over Google Cloud CLI. So basically, you can invoke Google Cloud CLI by clicking on this button, which should activate Cloud Shell. We click on that, and of course, you have to create a project. I'm not going to go over how to create a project because I assume, guys, those who enroll in this course already know the basics of cloud computing, Google Cloud, AWS, Azure, right? So we're just gonna dive into the advanced stuff immediately. All right, so once I activate the Cloud Shell, let's now start with the commands that are important in your investigation. Remember, this is only a quick overview of these CLIs. We will not dive deep into the how-to of every single command, okay? Let's now go back to the notes, which you already have, and we can, in cloud investigations, we start always with the identity and access management. It's worth mentioning that in Google Cloud, the command starts with gcloud, okay, followed by the service name, the resource you're investigating, and the verb. Very much similar to Azure CLI that we will see later, okay? So we start with gcloud and then the service. In our case here, when we want to investigate IAM, identity and access management, the service here will be IAM, okay, as this one, okay? The resource is the service accounts, and the verb is list. Let's start with the first command, okay? Here, it will show the identity and access management policy, but project-wise, or on the level of project. So here, I'm going to paste this command, and of course, the project here is natural furnace. I'm going to copy this and see the available IAM policy on this project. All right, so these are the key findings, okay, on the project we have here. Let me make this a little bit bigger. Go to text size, make this, it's too small. I mean, let's make it large. Okay, so that I can see the policy, the identity access management policy set project wide. Okay, so we have the members. This is the service account, and that's the role assigned to this service account. You will see service accounts and human accounts. Service account are, as you can see, highlighted with service account, or start with service account, followed by the actual value of the service account. And then you can see the role assigned to the service account. Here it's a service agent on the computer engine. Next, we have these are service accounts. Let's investigate the human accounts. These are human accounts, okay, are my own personal accounts. And as you can see, they are registered with the email address, and the role is owner. They own the entire project. So when you investigate cloud breaches, you start investigating the identity and access management policies on the compromised project. Okay. Next, we move on to listing the service accounts. I know we already know what are the service accounts here when we listed the identity and access management policy, but it's worth understanding the structure of the command to list only the service accounts. So we start with the G-Cloud, and then here the service is identity and access management. The resource is service accounts, service-accounts, the actual name, and the verb will be lists. Let's have a look at the service accounts. Of course, remember that this command will be executed within this project. If you want to change the project, you're going to have to specify the project name in the command. Okay, so here we have this service account, and disabled equal false. It means that the account is active, okay? And that's the display name. It's compute engine default service account. Now, this service account that starts with 61 and ends with 18 can actually be seen here. Okay, it has editor role and also has access to the cloud services and developer. So that's our service account here. It's one service account, but has multiple roles. After investigating and having a look at the policies and accounts in our project, we want to check the keys of the service accounts, because usually attackers, as you can see, when they investigate or when they compromise a cloud environment, they start after choosing the identity, they would manipulate the keys, deleting or creating new keys. So basically here, let's investigate the keys to the service account that we already found. We can modify on this command. So this command here starts with G-Cloud. The service is IAM, and the resource service accounts. The verb here is keys list, and the account is specified with --im -account followed by the actual account name. Therefore, here my account here, this account is actually we have to change it. So basically here, I'm going to investigate this account. So I'm going to copy this, and with the command, we're going to remove this account and have a look at the keys. So this account, this is the key ID of this account, and this is the actual timestamps of the key when it was created and when it expires. Okay. Now, of course, after you guys saw this, I'm going to have to change this key, right? So when investigating cloud breaches, I'm going to have to take a closer look at when the key was created and when it expires. Okay. Usually, the keys you have created as a SOC analyst or as administrator, it will be way back before the cloud or before the breach. So if you see new dates here, okay, it's actually suspicious unless you know that the administrator has created these keys. Okay. All right. Next, after we investigated the users, the service accounts, and the identity access management policies, we move on to investigate the compute engine. The first thing we investigate the compute engine is listing the current instances. Okay. I know we can do it from the GUI, but it's actually useful if you understand how to do it from the CLI. So G-Cloud, the compute is the service, and the instances is the resource name, and the verb is list. And we list the current instances we have in this environment. You see we have one instance named rack VM2. That's the zone, it's in Europe. That's the internal IP, and that's the external IP addresses. In cloud breaches, our aim here is to find out if there is any rogue instance or an unknown instance that we know we did not create. If there is, we should proceed and, of course, first investigate why this instance was created, and then we can delete it. Now, after listing all the instances we have in this project, we can describe the instance, getting basic information about the instance. So here we can copy this command up until the instance name, because we can change the instance name and add our instance here, which is rack VM2. Did you mean zone Europe West 4? Yes, that's my instance. Could not fetch resource. Yes, because this could be on another project. The resource projects, natural furnace, zones, Europe West 4B, instances, rack VM was not found. And that's because I am living here in a different project, or let me see. So check the compute engine, VM instances. So it's already here. However, we could not describe it. Let's have a look. The name is rack VM2. Oh, we specified different region. You see the actual region is 3-A, and we said yes to 4B. This is not the correct region. You can re-execute the command and say it is This region, 3A, not 3B. No. Okay, let's have a look. So indeed, now we can see all the info about the instance. For example, we can see the CPU platform on the instance, when it was created. You see it's very old instance back in 2020, and deletion protection is false. This means that I have not enabled deletion protection, which means when I delete the instance, the disk associated with the instance will be deleted. And here we can see the disk assigned to the instance, the size, and other information. Of course, other information are hardware information about the RAM, the SSH keys. I'm gonna hide this because, and scrolling all the way down, we can have a look at all the information about the instance. Next, we want to check the firewall rules. Usually attackers manipulate firewall rules, especially when they create a new instance. When they create a rogue instance, they will create a firewall rule that allows incoming connections to this instance on a specific port or outgoing connections using a specific port because they want to manage the instance remotely, right? So it's worth checking the firewall rules. So here, gcloud compute firewall rules. Compute is the service, and the resource name is firewall rules, and the verb is list. Let's see how many firewall rules we have, and we have to have a look here at the any weird or strange firewall rule that could exist. So basically here, this is default allow HTTP. This allows incoming connections, you see, on port 80, especially useful if you have websites in your instance. Default allow HTTPS, direction ingress as well, 443. These are rules created by Google, okay, by default. Whenever you create a project and an instance, these defaults or these rules will be created for you by Google. Now your job is to identify if there is any strange rule. This one, for example, allows incoming connection to on port 443. I don't see any weird rule here. Sometimes weird rules, you can, in an environment with a lot of instances and a lot of rules, it's very actually kind of exhausting to go over all the existing rules. So what you can do here, you can execute this command and use a grep. You're looking for specific ports based on your threat hunting campaigns or specific IP. You can add the port or IP here. For example, port 4545, it's a maliciously used port all the time. Okay, let's execute. We have no matches. All right, if we type now 443, we know that 443 exists, but we want to take a look at how the grep works its magic on the existing firewall rules. We cannot find all the available rules where port 443 exists. So it means we have firewall rules that use the port 443. Allow 443, that's the firewall rule, and it is allow. These are the rules that you created as an administrator in your environment. It will not apply the grep command on the existing rules created by Google Cloud, aka the default rules. Okay, dokie. Here, what do we have again? So next instances, you see IAM. Now we investigate the buckets because, as you know, guys, the three most important aspects in any cloud breach is the identities, the instances, and the buckets. The buckets usually are investigated to find evidence of ransomware infection or exfiltration, data exfiltration. So why do we list the existing buckets? Because usually attackers create new buckets, okay, so that they can exfiltrate data or add data to the project. Let's have a look at the existing buckets of this project. I don't think I have any existing buckets, but we can still execute the command and find out. Indeed, I have 0 buckets in my project. Excuse me, guys, I did not create any buckets. So here, this one, inspect the permissions. So basically here, we add the buckets to the command, and then we use get IAM policy, and followed by the name of the bucket. This is the name of the bucket. You see the bucket name follows this formula, GS, and then it's like very similar to HTTP, right? Treat this as a URL. So instead of HTTPS or HTTP, you add GS and then the name of the bucket, and you'll be able to see all the permissions assigned to the bucket. We will see the practical scenario, how important it is to understand and to extract permissions from the existing buckets when we discuss the lab section, where we will talk about actual breaches or actual cloud breaches. So if you work with AWS, Azure, GCP, SaaS platforms, or identity providers like Azure Active Directory, then this matrix will be or becomes our compass. This matrix basically shows how adversaries operate in cloud environments, what they target, how we can detect, block, and respond to those behaviors. All right, so let's first ask the question, what is the MITRE Cloud Matrix? As you can see, guys, the MITRE Cloud Matrix is a domain-specific extension of the MITRE entity and CK framework. We know that MITRE Enterprise covers endpoint, Windows, Linux, and network focus techniques. However, Cloud Matrix here focuses on cloud tactics such as identity and access management attacks, cloud control plane abuse, and a lot of other attacks such as SaaS exploitation and token theft and misuse. So in cloud, hackers do not need malware to gain persistence. Let's reiterate this fact. Okay, they exploit permissions, tokens, identities, roles, and serverless functions. They do not need to have a single they do not touch a single virtual machine here. So this matrix helps SOC analysts understand those cloud native threats clearly. So it's better, guys, to get yourself familiar with the MITRE cloud matrix so that you can map the incidents in a professional fashion. We're going to start first with initial access. You see, guys, initial access in the cloud rarely, as we said earlier, rarely starts with malware. As you have already known throughout the course, we already told you guys that cloud attacks or initial access starts always with identity compromise. It is your identity and access management plane the target all the time. For example, let's have a look at this scenario. A hacker finds an AWS access key on, say, a platform like GitHub, right? They immediately enumerate identity and access management roles and S3 buckets just using the AWS access key. They do not, no endpoint EDR sees anything here. This is purely control plane activity. Okay, that's how initial access happens. Next, after initial access, well, attackers move on to execution. And here we come to the execution tactic. Cloud execution is not about also running binary files. It's about triggering functions, basically cloud functions. What are the cloud functions we have here? We have Lambda, we have CloudTrail, we have GCP functions, Kubernetes, API commands. These are typical cloud functions the attacker trigger after they gain initial access. Another important tactic in the cloud matrix is the privilege escalation. So privilege escalation in the cloud, again, it's all about permission pivoting. We know in endpoints, Linux, Windows, Mac, it's also about permissions because attackers achieve privilege escalation well by sometimes, not all the time of course, by manipulating misconfigured files and directories. Here they take advantage of misconfigured permissions as well. For example, they exploit overly permissive identity and access management roles, and also there is a very popular role attackers abuse. It is the IAM pass role, and we're going to see why in the labs. So here the attacker does not escalate on a machine again. Okay, they escalate across the permissions and the APIs. Next on our list of tactics is the defense evasion. Here we have a lot of tactics or techniques under defense evasion, such as disabling cloud logging. We've seen in the cloud platforms, cloud logging depends on CloudTrail, in AWS Sentinel, in Microsoft Azure, and GCP logging in Google Cloud logging. They also try to avoid using temporary credentials and tokens, and of course, it is the hacker's footprint clearing logs or creating separate logging buckets. Example is, attacker turns off AWS, let's say not CloudTrail, GuardDuty in a new region. Let's now move on to credential access. So in credential access, cloud credential access actually, or theft, let me call it, focuses on stealing authentication tokens. That's what happens most of the time. Additionally, extracting secrets from environment variables. So here, cloud credentials allows the attacker to have full control of your environment. Then we have discovery. Discovery tactic actually is noisy in the cloud if you know what to look for. This one is easy to spot because it's easy to spot when attackers enumerate aspects such as your IAM users, roles, and groups, or S3 buckets. These enumerations generate signature patterns you as a SOC analyst or you as a SOC team can detect and hunt for. So discovery is easy actually. Lateral movement. In cloud, well, lateral movement happens via, most of the time, assumed role in AWS. If you're talking about AWS, and in Google Cloud, it happens through GCP service account impersonation. In Microsoft Azure environment, it happens through the OAuth consent phishing. So here, as you can see, guys, no RDB involved and no SMB. Lastly, or we have just two left, collection and exfiltration. So collection exfiltration is the last objective on the attacker's playbook. Most cloud breaches basically end here at collection and exfiltration. It's where the attackers perform the last action. So most of the time it is dumping the contents of your S3 buckets, exfiltrating data, sometimes exporting database snapshots, or syncing file shares. And the last tactic here we're going to talk about is the impact. Impact outcomes in cloud environments is actually not easy to tolerate for most enterprises, because here we're talking about ransomware, exfiltration, crypto mining that affects your entire cloud infrastructure. So for example, ransomware happens via storage encryption. Also, we are talking about deleting backups or snapshots and even crypto mining deployments. Here, hackers maximize profit using your own cloud build. That's a disaster. So now, after we have talked about the tactics, let's now talk about real incident mapping and used our knowledge to map a real incident to a cloud matrix. For example, when we talked about initial access tactic, what is a real map for this tactic? Well, most of the time it is a developer committing AWS keys to GitHub. That's a very popular scenario we see a lot in cloud incidents. Developer forgets keys in GitHub, not specifically AWS. And then the discovery comes here after attacker discovers the keys at GitHub. Attacker tries to enumerate buckets and identity and access management roles. Then after the enumeration finishes, hackers move on to privilege escalation. So here, most of the time it is misconfigured trust policy, okay, allows role assumption. So they create identities, they assume roles that are expansive in your cloud environment. Then comes persistence. Hackers, for example, creates a new hidden access key or hidden identity. And then defense evasion. Defense evasion here, attacker deletes, of course, CloudTrail logs in a new region. And then when collection comes, they dump S3 buckets containing, let's say, customer data. And when the impact, when we talk about impact, let's say deploys crypto miners across Lambda functions. You see, this behavior perfectly aligns with the cloud matrix techniques. This helps SOC teams build detections, alerts, and playbooks. CloudTrail is not just logs. Most people think it's logs. It's AWS authoritative record of who did what, from where, and when inside an AWS environment. Every CloudTrail event is the security source for a lot of things that, as a SOC analyst, you want to investigate. So CloudTrail pipeline has 5 major components I want you to take a note of. First, you have the event generation layer, the event aggregation and processing layer, and then you have delivery and storage layer, and lastly you have the analysis layer. Basically, the analysis layer is the CloudWatch, the Athena, and the SIEMs. That's actually your high-level blueprint. Event generation layer. This is the first layer where CloudTrail captures the raw activity. AWS generates 3 types of events. First, the management events. In the management events, we see the control plane actions, such as creating users, updating roles, modifying buckets, changing security groups, starting EC2 instances. These are the most important for us as SOC analysts. The next type of events in AWS generates in the event generation layer is the data events. These log high volume resource level operations. For example, S3 object create or delete, and also it tackles Lambda function invokes and Dynamo database item level API calls. By default, they are off, okay? But, because they are actually expensive. But for investigations, you might want to consider these or to turn them on because they are gold in investigations. And the third type of events AWS generates in event generation layer is the insights events. These events detect anomalous behavior using statistical models, like, for example, unusual user behavior or API spikes. They only appear when AWS detects something that's out of abnormal. So once events are generated, AWS starts normalizing them into a standardized JSON structure. And here we have to focus a little bit, because at the end, when you respond to cloud incidents, you're gonna analyze logs written in JSON. This step is very critical. CloudTrail enriches the raw event with metadata, such as AWS account, where the action occurred, the identity, error codes, region, and we'll see a lot of them when we analyze the logs. Then AWS batches events internally before sending them to the delivery pipeline. Next layer is a delivery layer. Here, the CloudTrail delivers logs through 3 main channels. So the first channel is, of course, you know it, I know. It is the S3 buckets. This is the immutable archive. Events are delivered in compressed format inside structured prefixes. These kind of events or these kind of files are ideal for actions such as forensics and maybe even long-term storage if you have laws to comply with, and of course SIEM ingestion if you want to upload them to SIEM tools like Splunk or ALK. All right, now let's get back to the layers. Let's talk about the storage layer. So here, the primary storage consists of S3 bucket with versioning, lifecycle policies to Glacier, and of course, server-side encryption like SSE S3 or SSE KMS. I think you guys are familiar with these terms because at the end, this is a cloud SOC course, not cloud basics course. Now, there are optional enhancements to storage, such as maybe object log. Object log basically protects against an attacker attempting to delete the logs. And of course, another enhancement is the MFA delete and cross-account log storage for centralized security teams. So here, CloudTrail becomes tamper evident. Okay. All right. Now, how CloudTrail logs are structured? Let's talk about a JSON event here. So each CloudTrail event is a JSON object, okay, with several top-level fields. For example, the field here, event time, indicates when the action happened. Event name indicates which API call was executed. User identity indicates the real identity of the action. These are of utmost importance, and you should have a note, maybe, or a reference where you'll be able to see all these fields and their meanings. Now let's talk about the analysis layers. Once logs are stored, SOC teams start to analyze them through a lot of tools, multiple tools. First, we have Athena. In Athena, you can do SQL queries on S3 stored logs that are stored in S3 buckets. You can analyze them with Athena. It's actually perfect if you're doing a large investigation or if you're doing indicative compromise sweep. Additionally, if you want to do timeline construction and find all the actions by a suspicious IAM rule, you can use Cloud or you can use the Athena. The other tool is CloudWatch. CloudWatch is used for real-time detection, like alerts, thresholds, ingesting into SIEMs, and pattern matching on fields. The third tool in the analysis layer is the SIEM platforms. Okay, Splunk, Sentinel, Elastic, you know the drill. These systems correlate CloudTrail with, for example, EDR telemetry, S3 access logs, GuardDuty, VPC flow logs. This is where the detection story becomes actually complete. And lastly, to sum this up, take a look at this lifecycle. You see here, we have the architecture that enables modern cloud investigations. First, we start with the user making an API call, then the CloudTrail that goes into the CloudTrail event generator. Then we have the event normalization and metadata enrichment, and then the batch processing starts. After all the processing and enrichment of the event that the user created or at least invoked, we start delivery. Delivery goes into S3 buckets in an archive form, and then into CloudWatch for real-time inspection, and in Event Bridge for automation. After the processing and delivery is finished, we can start the analysis using Athena, SIEM, or detection pipelines. If you understand this flow, guys, you can reverse engineer any attacker's path. All right, now let's have a look at an example CloudTrail log file. And what's better than looking at the AWS documentation? So here, the cloud log file name format. And this is actually simple. We're going to now take a look at the actual log file. So here is an example, Amazon EC2 log examples. You see, in AWS, all CloudTrail log files are actually or follow the same standard. Every cloud or CloudTrail records, basically, every API call made in your AWS environment, whether it is through an AWS console, a CLI, SDK, or even internal AWS services. You see, each log file is a JSON object with a simple structure. So it starts with the records array. Inside the records array, each object is one discrete event. Let's now break down the most important fields you will investigate as a SOC analyst. So we start with the event version. This tells you guys the schema version of the event. In our case here, it's 1.08. It's not useful for detection, but sometimes it matters for log parsing. Now let's have a look at the next field, user identity. So user identity is one of the most important fields you want to focus on. It answers the question, basically, who performed the action we're investigating. In our case here, we can find it by looking at the ARN of the user. Here it is Matthew. This is the user who performed the action or the API calls. So from this structure, as you can see, you can identify what was the request done by an IAM user. In our case, it is done by an IAM user, judging by the type. Is the user root? You can answer this by looking at the ARN, right? Is it a federated identity like an SSO or SAML? Okay. And of course, we got to see here the session context. This is crucial because it shows the MFA usage, the role assumptions, and session creation time. Okay. Now let's have a look at the next one, event time. This one is simple, right? This timestamp, it is actually in UTC format. Okay. SOC teams basically correlate this value of the event time with other log formats or the logs like GuardDuty, VPC logs, or system logs to build what we call the timeline. We discussed the timeline when we talked about the cloud investigation framework, if you remember. So that's how you build the timeline. You look at the event time if you're investigating AWS. Now let's look at event source and event name. So these two fields together, event source and event name, describe what actually happened. So if you take a look here at the event source states EC2 Amazon AWS.com. So this is an instance activity. And the activity is stated by looking at the event name. It is start instances. In other cases, you could see something different. Like, we have a look at this one. This is also EC2. EC2. This one, I am Amazon AWS, which means this is an identity creation event, create user. Also, it could be related to buckets. Scrolling down, you should see an example for buckets. This is the CloudTrail, the logs. All right, there is no example for the buckets, but if it is a bucket activity here, let me scroll up and show you guys. Instead of EC2, you will see S3. If it is a lateral movement, you will see STS. So here the event store allows you to see what kind of activity is taking place in your cloud environment. So that's the place where your detection rules often start, here, okay? All right, let's talk about now the AWS region. Well, this is the region of the API call. In our case here is US East 1. Basically, you should build a baseline of what are the acceptable or the expected regions where the API calls are used, basically. Unexpected regions, like something different from US East, depend on your environment, right? If, for example, here, most of them are US East. If you scroll down, you can see it's also US East. If you see something like SA East or Asia, this is unexpected behavior. We should flag it. All right, now let's look at the next field, source IP address. Well, this is also self-explanatory here. It shows the IP address where the request originated. In our case here, it is 1.192.0.2.0. Well, this field actually becomes critical for discovering suspicious login events, impossible travel, and of course, the later we will see it has to do with Lambda function executions. Okay, so this is also one of the important fields you want to focus on. Next, we take a look at the user agent. So this field basically reveals how the API call was made. In our case here, let's have a look. So AWS CLI. This means that this action was performed through the AWS CLI. We just looked at in the beginning of the course. Okay, if you see something like instead of CLI, you could see something like console, which means it is the AWS console that launched the action. You could see SDKs, or you could see something different that indicate scanner activity. So also we should focus on this field. Okay, to the fun part, request parameters. So this field, guys, includes all the parameters sent by the user who took the action on the API. Under the request parameters, you can see we have instance set, and we get the items instance ID mentioned, or two instance IDs mentioned here. So under the request parameters, you will see the detailed information related to the asset or to the event that was called. Since this is a log file that details the actions taken on an instance, by creating an instance, under the request parameters, you will see parameters related to the instance, such as instance ID that was created and so on. Below that, we can see the the response elements. So here shows what AWS returned when the user created the instance with these two IDs. Sometimes AWS basically, guys, hides sensitive data. However, this is useful for confirming whether the action succeeded. So basically here, since we see request ID and the instance set with the items, here we have the ID here indicates that this is a pending instance. Here we got it. Code 0 pending, code 84 star, and instance ID with instance CB, it is also pending and stop. So by looking at the request parameters and response elements, you'll be able to see detailed information about the resource that was used and whether it was successful or not. Error code now. Let's have a look at error code. I want to discuss error codes with you, so let me see. Request ID, event ID. Okay, so we don't have error codes here. Let's look at another sample log file. Let's move on to these fields. So here, one of the fields I want to highlight is this recipient account ID. Of course, here, remember, everything we discuss in this course is from the perspective of SOC Analyst. This is not a cloud computing course, okay? So here we have recipient account ID, and it states this number. This is actually useful in multi-cloud environments or multi-account environments because, guys, it helps determine which account received the action, not requested the account that received the action here. Remember, our action here is creating the instances. Okay, and here we have the event ID. So each event, guys, has a unique UUID here. It's useful when you need to cross-correlate with AWS logs or SIEM logs. So these data, event ID and recipient account ID, are useful for log correlation. Also here we have read-only. So this shows whether the event modified resources. And the value here is false. So when the read-only equals to false, it means that the action performed on the instance was either create, delete, or update. Okay. When you see the value here equals to true, it means there is no modification whatsoever done on the instance. Okay. It may be just list or get or describe actions. Okay. So most SOC teams basically prioritize alerts on operations that involve write or create, such as this one. So this one start instance, and the read only is false, which means this log file should be prioritized and investigated, because false indicates that it wasn't just read only, it was more than read. Create, delete, update, write, whatsoever. And we have the management event. So the management event here value states true. This field, okay, modifies the AWS infrastructure. Also, you have, instead of management, you could see data event here. Let's search for data event. Let's copy this and search for data event. Okay, there is no example of data event. It's fine. But you see, remember that when you see management event, it means that a management event modifies AWS infrastructure. And here it is true. It means that this action modified an infrastructure resource on AWS. When you see instead of management, you could see data here, data event, okay, which indicates like something like S3 get object or Lambda invocation. Something has to do with these resources. Okay, and now let's touch on the VPC flow logs. Okay, these are important because it allows you to see the traffic logs in your AWS environment. So basically, we're going to have a look at a couple of sample entries so that when we analyze large log files, we'll be able to understand what we're doing. So let's have a look first at this example. I know they don't look that nice, numbers, you know, and so we're going to break it down, no worry. So here where you see a sample of flow log entry here, it's important to understand where to look. Okay, so here, let's start with the IP addresses. I'm not going to look at the ID here. We're going to start with the IP addresses and the ports. So here we start with the source IP, destination IP, source port, destination port, okay? And this, guess what? This is the protocol, okay? And then what matters after that is the result. Here, the result is denoted by the accept and the OK here. So what happens here? The source IP address that ends with 39 sent a request to the destination IP address that ends with 21 on source port that ends with 41 and destination port 22, which means that this is an SSH request or SSH connection attempt from this IP to this IP. And the protocol is TCP, 6 means TCP, okay? And the result was an acceptance of the connection. Judging by the accept, traffic is permitted. The accept means not the SSH was accepted. It means that traffic was permitted in your AWS. It means the IP address here was allowed to send an SSH request to this IP on port 22. That's what accept means. It doesn't mean they logged in. It means they were able to send the request from the network. And OK, it means that the log status is valid. Let's have a look at the rejected pattern. Here, have a look again. Data source IP, destination IP, the source port. Destination port here is 3389. It means that this is an RDP traffic. Okay. We look at the result, it is reject, which means that the RDP traffic was rejected from this IP into this IP. So the accept or reject is actually controlled by your security rules in your AWS environment. When you create security rules for access control and firewall rules, they actually dictate what is allowed and what is disallowed. So here reject means the security group or maybe a network access list denied the traffic, either in your environment or in their environment. Okay. This is useful basically in SOC to spot failed access attempts. Let's have a look at the third one. So in the third one here, no data skipped and records. Following are examples of default flow log records. In this example here, no data was recorded during the aggregation interval. So here, during this investigation window, the interface production or produced no traffic. So here there is nothing to log. How do we know? We look at this. There is no data. No data means no flow observed. Okay, let's have a look at another one. This one, yeah, skip data. So skip data, basically, it means that flow logs couldn't capture data during the interval due to internal capacity limits. So here, skip data means that the interface actually generated traffic, but the logging system in your environment or the logging system skipped the recording of the log, possibly maybe because of limits or capacity limits, possibly here losing multiple flow entries. You should investigate the skip data when you see it in VPC flow logs, because it may, I'm not sure, it's not basically definite conclusion, but it may indicate or hide malicious or unexpected traffic. Okay, these were sample VPC flow logs and how to analyze them. When you look at these and understand them, you will be able to interpret other log entries in your VPC log environment. We're shifting into Microsoft Azure, and we're going to dive into two of the most essential logging sources for identity-first security. And these log sources are Azure Activity and Azure Active Directory sign-in logs. If you can read these two log streams with confidence, you can detect 80% of identity abuse and hacking attempts. So let's start first by understanding what each log type really captures, because unfortunately many SOC analysts still confuse them. So let's start with Azure Activity Logs. Azure Activity Logs track what happened inside Azure resources. Think of them as Azure's control plane logging, okay? Here we can answer questions such as who modified a virtual machine, okay? Who changed a network security group? And other questions such as who elevated privileges on RBAC or role-based access control. This is very, very similar, guys, to AWS CloudTrail management events that we talked about earlier, okay? Now the next log source is the Azure Active Directory sign-in logs. Here we track authentication events only, like who logged in from where, which app, was MFA bypassed or passed, and did Azure Active Directory flag this login attempt as risky or not. Let's now focus on key fields we as SOC analysts must track and understand. First, we have the caller or the identity. Here we show, or this field shows the principal who triggered the action, okay? If it is a service principal, well, we're gonna have to check if the service principal is compromised or not. The next field is operation name. Operation name indicates the API call, such as Microsoft Compute or virtual machines, right? This is an example API call. 3, the category. Now, the category field includes a lot of subcategories like administrative, policy, security, resource health, or service health. The fourth field is we want to get familiar with the result type and result description. These detect failed attempts or even enumeration attempts. Also, we have correlation ID. This field is used to stitch multi-step operations all together. And of course, we do not forget the properties field because it contains detailed request parameters, which is very crucial during forensics. Now let's talk about attack scenarios that are visible or can be viewed in activity logs. For example, a log admin creates a backdoor user. This can be viewed in activity logs. You can see it. Attacker reducing MFA requirement policies. Also, attacker deleting a log analytics workspace. Another example is compromised service principal spinning up crypto mining resources. This is very common in cloud environments. Ransomware actor deleting snapshots before encryption. These are high impact events, and activity logs basically expose every single one of them. Let's talk about critical fields you see in sign-in logs. First, the user principal name. Usually this is the target of authentication. Okay, it's clear, you know it. IP address, also clear, used for IOC correlation. The location can be used for Microsoft geo-IP mapping. Client application used. This can be mapped to examples such as browser, mobile apps, and legacy protocols. Authentication details. This answers the questions such as what factor was used, did MFA succeed, challenged, or was risk-based conditional access triggered. Also, you have conditional access status. You can see key values here such as success, failure, applied, not applied, enabled, not enabled. This basically tells you whether policies protected the identity. And lastly here, risk level aggregated or risk level during sign-in. Here we see machine learned risk scoring from Microsoft. So now let's talk about a real workflow here. How SOC analysts actually use these logs. Well, first, we have or we start with hunting for suspicious sign-in activity. Okay. For example, we look for MFA skipped, legacy authentication used, new OS or device recorded. Next, hunting for privileged escalation. Of course, here we focus on activity logs. Fields we want to look at are role assignment write events, service principal credential write, application role assignment, and directory role changes. Again, guys, we cannot explain every single field and what it means, because the course will be like, it's not going to end in a year, right? You can get back to the documentation of Azure to understand what every field means, or you can get back to the course notes. 3, we hunt for persistence. And this includes things such as new automation runbooks, changes to conditional access, and a particular mention here is adding new credentials to service principals. 4, we hunt for data access. Sign-in logs show identity access patterns. And remember that activity logs show administrative changes enabling that access. So as you can see together here, they complete the entire puzzle. All right, guys, now it's time to look at Microsoft Azure audit logs. So in the screenshot here, the audit logs have been ingested into the log analytics workspace. You can choose to ingest the audit logs in Microsoft Azure, maybe to Event Hub or to log analytics. Okay. The preferred method, of course, is the log analytics because it's easy to navigate, and well, I prefer it more than the Event Hub. So that's what you could see in a typical log audit log from Microsoft. Of course, here you've got the chance to run a query. For example, this is the query that was run against the logs. We can explain them and break them down in a simple fashion. So let's start first. What do you think with the actual query that was run in the logs? So here we have the service name, okay, and it contains entitlement.audit. This means that the logs shown here represent entitlement management operations. These are the operations typically involve things such as adding, removing, creating users and groups. Okay, they are under the Microsoft entitlement management operations, and they can be queried by using this query. Specifically, we're talking about entitlement or entitlements.audit. This is actually crucial in your SOC because you want to monitor identity changes in your Microsoft Azure. You do that by auditing or by querying the entitlement audit logs. Let's start now with the fields here. We start with the service name because the location, time, and category are self-explanatory. We start with the service name. Here, the service name states entitlements.audit. This is exactly what we wanted to query in the first place. It refers to Microsoft Entra, again, entitlement management. Okay. You see, guys, these logs here, all of them, they track governance activities. Here we see the operation name that states the activity, adding member, removing member, creating and removing groups. Okay. Next, we move on to the next one, which is the operation name. Here it tells you guys what exactly happened. Okay. So here, the first one indicates that a member was added. However, this doesn't mean that a user was added. It means a member was added to a specific group. Okay. This basically reflects authorization and identity lifecycle actions inside Entra ID governance. Next, we see the data partition ID, and then we have the action. This is also important. The action field shows how the operation modified an object. In our case here, what it did, it actually updated an existing object, which is the group, by adding a new member. So update, a change was made to an existing group. Then we have here, the next entry shows delete. So delete means a member was removed or even a group was deleted. But here it states that a member was removed from the group. Another action could be update here. Create. Do we have create? Yes, create here. So create means a new group or object was created. And indeed here it states that a new group was created. Now let's have a look at what appears when we expand a specific log entry here. You see, we get the message as shown here. This is the message. The message field is a detailed audit description of what happened. So in the example here, we have add entry users.data lake admins add to group uptrusted as member. This message explains in plain language which identity was added. In our case here, it is the data lake admins. To which group it was added to uptrusted group. And in what role? The role was member. So here, this is the role. And this is the target group. the affected one, and that's the group that was added as a source group. This is the most useful field for your SOC investigation because it describes the exact identity change. Then we have another important field we want to look at, which is the result type. Let me do it like this. I think it's better. We'll choose maybe another color, red. The result type here, it indicates a success. Okay, success means that the change was actually applied. Okay. Sometimes it's not success. Sometimes it shows failure. Failure means the operation was not permitted. This is basically useful for detecting suspicious attempted privilege escalation. Then we have, let me see, the request ID here. This is a unique ID also for the event and can also be used for correlation with other log sources. Okay. What else we have? Choose another color. Okay. We have this resource ID. So basically, the resource ID shows the Azure resource path where the change occurred. That's the path. That's where the change occurred here. This allows us to understand which environment or resource group the change affected. All right, so that was a sample, a Microsoft Azure audit log file, and the explanation of the fields. All right, let's have a look at the Microsoft Azure sign-in logs. Basically, these are found under Microsoft Enter ID monitoring section, and here sign-in logs. It's crucial to monitor these logs for unusual sign-in attempts to your Azure environment. So here, it allows you as a SOC analyst to verify, was this login expected? Is this user active? Are there suspicious patterns? Okay, you could spot this by looking at the user. Next, we move on to the application. So here, this is the Azure AD protected resource that the user Isaac Schmitz attempted to access. So here it is Microsoft Application Access Panel, which means the user trying to access the Office, or in other words, Microsoft 365 Access Panel. In another sample here, we have Emma is attempting to access the Medina Portal developer, which is a basically custom enterprise application. This actually helps us as SOC analysts identify the target or the targeted resource in the authentication event. Let's now look at the other field, which is status. So here, this is the outcome of the sign-in attempt. Success indicates that the authentication completed. Interrupted means that the login was disrupted. It wasn't complete, okay? Maybe because the network problem, MFA failed, blocked by rules. You have to correlate this with other logs, maybe with the access control logs, okay? So us SOC teams usually or often treat interrupted here events as potential early indicators of failed login attempts, failed MFA or conditional access enforcement. We should investigate this interrupted. Also, success are not ruled out of the equation because attackers sometimes are able to successfully log into your environment, right? So we have to correlate this with other data from the who the user, the date, the timestamp. Is it during usual working hours or outside? So that also is important or of equal importance in your analysis. All right, next, let's look at the IP address. So basically here, this is the public IP the user used to authenticate. So here, why the IP address is important? Because it is basically essential for correlating events such as impossible travel, session hijacking, login attempts from unusual geolocation, or maybe even it can allow you, or it allows you to spot VPN usage patterns. And lastly, we have got the location. So this is geolocation, the Microsoft resolved the IP from. So here, basically, usually when you look at the location, we think of anomalies. Usually location anomalies are used in identity protection risk scoring. Okay. Here we basically try to detect stolen credentials, botnet logins, or unusual user behavior by looking at the location. Now in Google Cloud, we have 4 types of GCP audit logs. Each serves a different purpose in detection, forensics, and compliance. 1, we have the admin activity logs. In the admin activity logs, we see who changed what inside GCP resources, okay? Admin activity logs is always enabled, okay? And it's actually free and cannot be disabled. For example, here you can see identity and access management role changes, and also you will see firewall role modifications, VM logs, and API logs. This is your equivalent of AWS CloudTrail management events. If you still remember, I believe you are. Now let's talk about the next type of GCP logs, which is data access logs. In data access logs, we see records of accessing the data inside resources. For example, we see reading object logs, listing secrets, accessing file store documents. However, you should note that these are disabled by default, okay, to save money. If you want to enable it, you're going to have to tell your admin to enable data access logs in Google Cloud. Because I believe it's crucial for detecting secret exfiltration, object access during ransomware staging, and misuse of service accounts. The third type of GCP logs is the system event logs. System event logs are by default generated by Google, not by you, okay? I believe you guys, you know it. System event logs show internal system actions like auto-scaling or maybe even health checks. System event logs come useful, especially, I think it's also critical, especially when you want to investigate like VM tampering, compute engine failures. Also, we want to investigate unexpected auto-scaling events. All right, the fourth and the last type of Google Cloud event logs, it's the policy denied logs. Here you see log events blocked by organizational policies. This is actually a feature of GCP Organization Policy Service. Examples of these logs are denying external service account keys, blocking VMs without OS login, and also you will see logs of blocking public access settings. Now, let's talk about where GCP audit logs live. Okay, unlike AWS or Azure, Google Cloud consolidates most audit data into what's called as the cloud logging. Audit logs flow into cloud logging buckets, log analytics, especially BigQuery here, and log syncs for export. You can then route logs to, BigQuery for investigation, the PubSub for SCM or SOAR, cloud storage for long-term retention, and a Chronicle, which is basically the Google's version of SIEM. Let's talk about the anatomy of GCP audit log entry. So a GCP audit log entry is a structured JSON document containing everything a SOC analyst needs for reconstruction. For example, the proto payload. This is the core of the log entry. It contains fields such as the method name, the service name, the authorization info, authentication info, and resource name. This is where the investigation happens. You focus on the proto payload all the time. Next field is the authentication info. This is critical for identity-first detection. It can include details such as the username, the service account used, the token information, and identity federation details. If you see unusual service accounts here, well, investigate. 3, we have request metadata. This shows where the request came from, like caller IP, user agent, TLS info, and as you can see here, zone region metadata. This is useful for indicators of compromised sweeps, and of course, you want to do geolocation analysis. And now let's talk about event flow and architecture. Here's an example lifecycle of a Google Cloud audit event. You see it starts with user or service account performs an action. Next, identity and access management authenticates the action. GCP servers records the request. Okay. Then an event is created. The event transformed into audit log format for you to investigate. Cloud logging then ingests the event and then log syncs export to the tools we mentioned, SIEM, BigQuery, so on, so that you as a SOC analyst can start the analysis. Now let's talk about how SOC investigations or how SOC teams use these logs. Much like in AWS and Azure, we talked about the example workflows and life cycles of how SOC analysts should treat these logs. Now let's apply that to Google Cloud. The first scenario is a privilege escalation via identity and access management. Here, you should look at admin activity logs because it reveals the set IAM policy, the create service account key, and role bindings as well. So here, you will discover that attackers love service account key creation. And this is basically only visible in admin activity logs. Okay, so if you're investigating privilege escalation, we check admin activity logs. Specifically, we check these fields. Next, data exfiltration. Here we investigate using data access logs, like get or list actions on storage or secrets. We should also correlate with request metadata.ip, and we should create timeline of object reads. You see in Google Cloud Logs, most of the time, if you are working with the Cloud Logs right directly from GCP, from a GCP project, you're gonna find them under logging, and from here you can click on either Log Explorer or Log Analytics. This is where you will inspect your logs. However, this is useful only in small settings, right? as a SOC analyst, most of the time you would export the logs and upload them to your SIEM tool, or maybe create a connection to send the logs in real time to your SIEM. However, it is actually good practice to get yourself familiar first with the basic logging structure in GCP before working with them in a SIEM tool. So here we have under logging, Log Explorer, and Log Analytics. In Log Explorer, that's an interface here, we can run queries, actual queries here, using the LQL language, which is the language specific to Google Cloud logging, or used to query Google Cloud logs. So we run the query here, and we monitor the outcomes based on our query. These are the logs here, as you can see. And on the left, we can see the severity and the resource type being where the access is being logged. In my case, most of the logs are done, or most of the actions are done on the VM instances. Okay. In Log Analytics, the case is actually different. Here you will run SQL queries, okay, against the logs. So, for example, if I run the query here, I can expand this. You see, wait. So if I run this now, I can see the access logs, all the access logs I have. The type, okay, instance, bucket, whatsoever, the severity, and of course timestamp, and the payload, which contains details about the resource being accessed. However, if you want to modify the query, you can just click on SQL, and for me, it shows you the entire query that was being run. And here you can see the scope. First, it is the project scope, so it's running project-wide, okay? And if we scroll down, we can see the other fields that it is actually retrieving from the logs, such as the timestamp, the severity, the resource type, exactly what we are seeing here. From the scope query here represents the project, and it limits the output to 100 log entry. So these are the two main areas where you work with logs. Let's get back to Log Explorer for a bit and see an example query we can run here. So here, most of the resources being accessed are VM instances. Okay. However, every query you run here should start with a format. So all queries start with the field proto payload dot method name. Here I define the resource that I want logs for. For example, if I want to see all the modifications to the identity and access management, which is the most important in your cloud, you can use this value set IAM policy. Okay, so this will allow you to see all the this query allows you or catches any identity and access management policy modification, which is actually basically one of the highest risk admin activities. As SOC teams, we should monitor this to detect privilege escalation attempts, especially if performed by unusual accounts. If you run this, you see we have no outcomes because there are no notifications to any identity and access management policies in my account. Another important query is to track new service account creation, because hackers usually create service accounts to maintain persistence. How you can do that? You can keep this the same, protopayload.method name, and then you can change this to Google IAM admin v1 create service account. That's an example query to catch new service account names. If I run this, as you can see, there are no outcomes, which means my environment is still in the safe. No service account creation that I'm not aware of, and no changes to identity and access management policies, of course, that I'm not aware of. We can also detect service account key creation, okay, because a newly created service account key is a critical credential. Whenever it is created, you should inspect it. If an event, or if this event is unexpected, you should treat this as a potential account compromise. How can you do this? Again, keep protopayload method name the same, and you just change the method. Here we're still creating the IAM plain, and we're still creating service account. However, we want to only query service account keys. So we put here, create service account key. And of course, no new account creation keys. I can also query for the start and stop of virtual machines. So here, keep protopayload method the same. What we have to do here, if we change this, okay. So here, since I'm gonna use two conditions, VM start and VM stop, I'm gonna use two parentheses here. Inside the parentheses, I'm gonna use the first condition between double quotes, which is VM start. VM starts with V1 with compute instances start. That's my first condition. Next condition is or, okay, which is VM v1 compute instances dot stop. So if there is an event that started an instance or stopped an instance, it will now show up. And there is none in the last 5 minutes. Okay, why? Because I haven't stopped or started or stopped any instance in my project. You can expand, actually, by the way, the time duration retrieval of your logs from 1 minute to in the last 10 minutes. And that's basically still, I mean, you have to expand this sometimes. So for me here, I can set a specific time, okay, start time and end time. Let's say the start time, that also depends on the retention period, okay? Maybe you, in your environment policy, you cannot retain logs for more than maybe 30 days, okay? So this means you cannot retrieve logs from GCP that are older than 30 days long, right? That's why then you can have to export them and use offline analysis or SIEM analysis. For example, I can hit start time, choose, let's say September, and the end time is today. Let's hope I get something. It takes some time because now it's scanning a longer time span, up to 3 months. So it looks like we have found something. If I click, because I remember I have stopped one of my instances at least once in the last 3 months, so it must show up here. And I have found some results. So you see, guys, as you can see, we have 8 logs that show stop, start, or the start and stop of the instance, the email, and that's also the region of the VM. Okay, this is also critical, because this is useful for spotting unauthorized compute operations. If you see something that's uncommon, meaning you have not done the action or you don't remember you took the action, it means this is malicious. Okay, usually this allows you to detect malicious or unauthorized start or stop operations on VM instances, which is basically common in crypto mining or lateral movement scenarios. Let's now move on to the last example, of course, in the context of SOC, which is detecting public bucket policy changes. So here, my query will look a little bit different. I'm not going to use now method name. I'm going to have to use now request policy bindings. Okay, so protopayload will stay the same. Request policy bindings. Okay, the error disappeared. Bindings role equal. So here I want to see my query should find any event that made a cloud storage bucket publicly readable, which is also malicious action, and it is actually closely connected to a major data exposure risk. That's why detecting these changes of a bucket access from private to public is crucial in your SOC operations. So here I want to use roles slash storage object viewer. Okay, that's my first line. And next, other line is, again, I'm gonna copy this and paste it here, but change the role to members, all users. I want to see the changes to the public buckets or storage buckets, okay, to those that are changed to storage object viewer, indicating public access, and to all members or the users. Run this. Let's see. Of course, I'm querying in the last 3 months, but I'm going to stop the query because I am sure I have not changed any policy regarding the access type of my buckets. But that's a general query. Now let's move on to what is called as Amazon CloudWatch logs. Okay. Well, Amazon CloudWatch logs is very well-known service or console that you can use basically to run queries on existing log files in the cloud. So basically, when you got VPC logs, Lambda logs, ALB logs, CloudTrail logs, this tool gives you the ability to run queries on these logs in a very quick and fast method. You see, logs insights, I'm assuming that you are somehow familiar with the CloudWatch console and the log insights, but for just to remind you guys, log insights is a query engine inside CloudWatch. Okay, you can access it from here, CloudWatch console. It lets you run SQL style queries. We will look at in this documentation sample directly on AWS logs. However, it's worth remembering that this is not SQL. Okay, the syntax here is optimized for searching messy logs, large logs, JSON logs, multi-line logs, all the real world chaos. Okay, we deal with insecurity operations. Now we're going to talk about the core structure of the query. Okay, so most queries follow a specific structure when you want to run this in the CloudWatch console. So it starts with the fields. Okay, and then we have the timestamp, and then we have the message, and then you get the pipe, then you have the actions. This pipeline approach lets you build queries step by step, just like performing a forensic investigation. For example, the first query here, find the 25 most recently added log events. So as you can see, it starts with fields, and then since we are sorting according to the time, so we use the timestamp, okay, and here message because we are sorting the log events, and then after that we have the pipe, sort, and the sort is done is according to what? According to the timestamp field. And the sort type happens in a descending order. And then we do another pipe when we want to execute another query, okay, and we limit them to 25. You see, between every query, we have a pipe, okay. The first query, fields, okay, is done on these two fields, the timestamp and the log. Then we have another action is to sort these events, and then another action is to limit them to 25. Another example you could see here is instead of using maybe the sort, you could see filter, okay. And here, with filter, you will be able to filter by a specific keyword, okay. For example, this one here, it gets a list of the number of exceptions per hour. How? Because it is filtering the logs, okay, for the keyword exception. Whenever an exception or whenever the keyword exception is mentioned in the logs, we extract it using filter message like. And after we extract all the logs containing the keyword exception, or in the SOC case study, you could use error. Instead of exception, you could write error here to extract the errors. Then we have another action is to use a stats function and count them. Another sort function to do a descending order of the number of exceptions. Okay, so that is your structure. Between every action, you use a pipe, and then you define the logs early using the message. And if you want to filter using the timestamp, using the timestamp, and then you can use after the first pipe, you can define your action. You could use sort and filter at the same time here as this log file, this query states. So here we use filter and then stats or sort. You're not bound by only one action here, sort or filter, or maybe even sometimes stats or parse. You could use them all in one query, just separate them with a pipe. All right, before I move on with the rest of the queries, let's restate what each key command means here. So fields, okay, to display a specific data or specific field. And then we have the filter, basically to narrow down the results. And then you see the stats, it is to aggregate your data, okay? And of course, we saw sort, it is to order your findings, and limit is to keep your results suitable. That's most of the functions or the key commands you will use in your CloudWatch query. You remember that, guys, the CloudWatch query is a pipe, follows a pipe architecture, similar to Unix commands. So basically, you fetch the data, pipe it to a filter or sort command, or statistical aggregation, and then maybe you use another statistical aggregation. So basically, it's a pipe architecture. Remember this. Okay, now let's look at a sample for Lambda logs, how to query Lambda logs. So the first one here determines the amount of over-provisioned memory. Let's break this down, shall we? So first we have filter, the type equal to report. You see the CloudWatch log automatically tags Lambda log entries with the type field. Okay, so basically here it starts with report, which means runtime statistics like memory used, duration, max memory, initialization time. You could also see here instead of report, you could see values like start or end. So start is Lambda started and end is for Lambda finished. So here, since the value of the type is report, it means we're retrieving statistical information about runtime values, memory, duration, initialization time, and so on. All right, so here we only want to report lines because they contain Lambda's performance metrics, like, for example, the memory size and the maximum memory used. Okay, this ensures that the query basically deals only with metrics, not application logs. Okay, let's move on to the next one. So here we convert provision memory to megabyte and extract the maximum. How? You see here we start with at memory size. So here at memory size is reported in bytes. So dividing it or dividing by 1000 converts it to megabyte. Okay, so here we do some sort of conversion of a provisioned memory to megabyte because this value is by default in bytes, not megabytes. Okay, and next we use max. So using max allows us, or using max is effectively the same as selecting the unique value itself, since provisioned memory rarely changes across invocations. And the alias used here is provisioned memory megabyte. Then move on to the next line. This is our next line. So here we start by finding the smallest amount of memory ever used. So basically here, the max memory, or the max memory used, is the maximum RAM, the lambda, used in a single invocation. So if we take the minimum across all invocations, will tell us what is the smallest amount of memory this function ever needed, right? So this is actually very useful because it detects functions with wide variability and also very low utilization functions as well that may be over provisioned. Next, we move on to the next line. It starts with average. So here we calculate the average memory used across all invocations. You see, this gives you guys a realistic day-to-day memory footprint, the average function. Next, let's move on to the other line of using max. So we find the maximum memory lambda ever used. This also tells us what is the worst case peak memory usage. And the last line we calculate here using provision memory megabyte minus max memory megabyte. So we basically calculate how much memory is over provisioned basically. So basically here this final field calculated answers the question, the key cost question, which is always around how much memory we are paying but never been using. So here it finds the top 15 packet transfers across hosts. Okay. In other words, it identifies the top network connections based on packet volume. How it works. So again, here we start with stats. Okay. We aggregate basically the total packets per connection. So basically, we start grouping by the source address, IP address, and the destination IP address. After we group them, we sum the packets field for each pair. Okay. And the output will be the total number of packets transferred between each IP pair. This basically identifies the heaviest traffic flows. All right. Next, after we do that, we move on, or we pipe this into another key command. So here we sort by the highest packet count in a descending order. In other words, this sorts results. So the IP pairs, so the IP pairs with the largest number of packets appear first. That's basic. And the last one is limit 15. It is to limit to the top 15 flows, which basically shows only the top 15 busiest network connections. So this query is important for SOC analysts. Why? Because it usually identifies unusual network spikes and also suspicious data transfers, and may also allows you to identify, of course, depending on the context, the potential exfiltration attempts in your VPC logs. All right, let's take one last example of explaining the CloudWatch queries. All right, this one is useful. Queries for CloudTrail logs. So basically, in the previous video, we explained the CloudTrail logs file format and what each field means. However, you will not go over CloudTrail logs one by one. Okay, you will need a tool to query these logs and analyze them, which is very crucial in SOC environment. One of the tools you can use to query CloudTrail logs is basically the CloudWatch console. Basically, you will run queries such as these. Let's go over these or the first two queries. The first one, find the number of log entries for each service, event type, and AWS region. In other words, it counts log entries by the service, event type, and region. So it starts with the stats function. Count by event source, event type, and AWS region. Basically groups CloudTrail logs by first the AWS service. Okay, event source. Remember the event source we talked about in CloudTrail? And we said that event source indicates the type of service. Here we go. We're using it in CloudTrail, CloudWatch queries. So we group them first by the AWS service, then by the API action, event name, and AWS region by the region. And then we count how many times each combination appears using the count statistical function. This is very useful for seeing activity volume patterns across the environment. Okay. Now let's move on to the next query. Find the Amazon EC2 hosts that were started or stopped in a given AWS region. All right, so it starts with filter, okay? And these are typical fields you will see, or basically you already saw in a sample CloudTrail logs. We are now using them in a CloudWatch query. So here it filters CloudTrail logs to show only EC2 start or EC2 stop actions that happened where in the in the US EC2 region. This is useful basically for detecting VM changes or unexpected lifecycle operations. You see, we do not need to go over all these queries because it's enough to understand the basic structure of a CloudWatch query, and then you'll be able to apply them depending on the log file, basically. So here, these fields are actually variant depending on which log file you are querying, okay? So here, this example we already discussed in the previous section, okay? It is only for Lambda logs. You see in CloudTrail logs, the field become different because it depends on the format of the log file we are querying, okay? We already explained what the CloudTrail logs, and we will go over other log file types so that you'll be able to query them in an easy fashion. All right, so in Microsoft Defender for Cloud Apps, we start by understanding the difference between policies and templates. Okay, so here on the left, we have got a section for policies and a section for templates. Right now, we are at the policies section. Okay, the policies here are active templates that will produce the actual alerts in your cloud, in your Azure environment. This is where you create policies to produce alerts for threats. Okay, however, when it comes to the templates, which we're gonna go over, the templates actually are blueprints that can be used to create the policies. So here we create blueprints for the policies section. In the next section, we're gonna explore how we can create or start by creating a policy. So as said earlier, we can create a policy from the templates because the templates are the blueprint for creating policies. From this section, we can select a template and click on create policy. For example, here we can create a policy to detect logon from a risky IP address. Alert when a user logs on to your sanctioned apps from a risky IP address. By default, the risky IP address category contains addresses. So basically, these are the IP addresses categorized by Microsoft Threat Intelligence as risky ones. We can create actually a template. Based on this template, we can create an actual policy that will protect our Azure environment from risky IP addresses, okay, when it comes to logon. So once we select create policy, we can start by giving the policy a name, okay? It depends on what you want to name it. Next, we define the severity and a category of the alert. Of course, based on that, we can act different in the future. So basically here, this is the severity selected, and the category, basically, it is threat detection. That's ideal, okay? We then write a description, and then down here, we can create filters for the policy, of course, based on the attributes available to us. And then we actually we handle the alerts here. So basically here, the alerts always come up at the left side. But you can basically, guys, individually define if an email or text message should be sent. To avoid spam, okay, set a daily alert limit here. Furthermore, you can also send alerts to Power Automate like this. Now, when the policy detects a risky IP, here under the governance actions, we define what we want to do. Okay, here we have general controls over the actions. For example, here we can notify the user about the risky login attempt. We can also suspend the user. Okay, and also we can require user to sign in again or confirm the user has been compromised. All right, and that's also the same for Office 365. So basically, I would just go with all apps, okay, and create the policy. Another important setting to look in your Microsoft Defender for Cloud is the score metrics. Basically here, you can set your preferences on how Microsoft should rate the apps in your environment. Usually all applications in the internet are rated by Microsoft in this tool. However, you can control how Microsoft rates the applications based on key metrics you define. For example, you can set the domain registration, okay, the date on which the domain was registered, to maybe high. So here the value is set as medium. You can make it high so that Microsoft will give more importance and evaluation to the domain registration of the app, okay? And based on that, it assigns a risk factor. Let's now look at Microsoft Defender for Endpoint. So through Microsoft Defender for Endpoint, you can enforce application access, okay? Basically, you either allow or block access to certain apps from your devices. So here it says enabling this will block access to apps that were marked as unsanctioned and will deliver a warning on access and allow bypass to apps marked as monitored. So here are some explanations to what's going on. So we have unsanctioned, okay, and we have monitored. What does that mean? Unsanctioned and monitored are classifications you assign or tags you assign to applications in applications tag section. So in application tags, when you say an application is unsanctioned, it means that the application should not be allowed. And therefore, when you enable enforce app access in Bitdefender, or sorry, Microsoft Defender for Cloud or Endpoint, it will block that application. When you assign an app as monitored in the application tags and then enforce app access, okay, what's going to happen? Microsoft Defender will allow access to the app, but gives a warning, okay? And of course, the last value here, or the third value you can do is sanctioned. Neither unsanctioned nor monitored. You can set sanctioned app, which means that even if you enable enforce app access in here, the app marked as sanctioned will be allowed access, or the device will be able to access the app. Here we set alerts, okay, and send the notifications to email or through URL. Of course, that depends on your environment. So basically here, you can configure an informational alert to be sent whenever an app is blocked or accessed under a monitored status. Now, since cloud investigations are all centered around identity protection, it's worth talking about Azure AD identity protection. If you enable Azure Active Directory identity protection, alert integration, it will actually integrate your Azure Active Directory with Microsoft Cloud Application Security so that Microsoft Identity Protection will determine risk levels for the user or for the users who log in into your environment. It's basic monitor and alert process, okay? And it's useful, and maybe it should be mandatory to enable Azure Identity Protection if you have Azure AD on the cloud, of course, so that you get alerts whenever a user is rated, whenever a user sign in is rated as suspicious or malicious. You will get alerts. And of course, if you have any policies applied in the policy section we talked about, the policy will be applied and enforced. And of course, if you want to enable the scanning of sensitive labels, you can define this setting here under Microsoft Information Protection and Files. When you enable this, Microsoft will scan new files, especially those in your Microsoft 365 environment, for sensitivity labels. This is basically useful when you want to enable DLP, or data loss prevention. All right, now let's look at the most important section in Microsoft Defender for Cloud Apps, which is the activity log under investigation. This is where your SOC skills come into play, okay? So basically here what we see are logs from Office 365 and also from cloud apps such as Azure AD, SharePoint, Exchange Teams, and you could also see logs for SaaS apps in here, depending on your configuration and your settings, okay? Under activity, okay, we see the operation. So we have logon, we have failed logon, and we have also general failure. And we have also the reason here, like error validating the credentials. So we have under activity, the logon and the failed logon under this screenshot. And then under that, we have the user performing the activity. Of course, here I redacted the user because of privacy reasons, but it is actually visible. It's actually clear that this column shows the user who attempted the logon or received the failed logon alert. Basically, this helps you identify whether the activity is expected. Is the user part of your Azure AD, not part of your Azure AD? Is the user is expected to receive multiple failed logins? Okay. Also helps you identify whether a compromised account may be involved. A user is repeatedly failing authentication, as we can see here. So correlating the user with the activity helps you tremendously in your SOC investigation. Next, we see the application. So here, which cloud app the activity relates to. Under the screenshot, we have Microsoft Cloud App Security and Office 365. So here, this column helps us track cross-application behavior. such as moving between applications or suspicious activity patterns. Next, we have the IP address. And here, of course, it shows us where the activity originated from. Usually, SOC analysts rely on the IP address to detect suspicious activity, such as impossible travel, VPN deviations, or foreign logins. Next, we have the location. It's actually similar to IP when it comes to the investigation. And next, we have the device, desktop, mobile, browser, operating system. This helps you identify unknown devices, new device sign-ins, or device spoofing, or maybe even unusual access methods. And lastly, the date. Okay, this is the timestamp of the activity. This is also tremendously important for building attack timelines if you want to correlate with MFA events or conditional access events. Another section is the alerts. And as a SOC analyst, that's the section you will look at most of the time. Remember that alerts are generated based on the policies and the risk factors you actually configure under control. We talked about these, okay? So in the alerts here, we can now start looking at the alerts shown here. So the first one, we can see that a user, of course, redacted for privacy reasons with activity from infrequent country detected from here. So here, Microsoft Cloud Application Security detected a login activity, okay, from a country the user does not normally sign in from. We call this impossible travel, okay. Usually, Microsoft Defender for Cloud Security builds a behavioral profile for each user in your environment. If logins occur from a new or historically rare country, what's going to happen? It's going to trigger an alert here, okay? So as a SOC analyst, what does this mean for you? It means this could be an indicator of stolen credentials for the user who's attempting to log in, VPN proxy use, or compromised session tokens. An investigation is warranted at this level, okay? Next, we see here impossible travel activity. Also, this alert has been generated for the same user. And here, under apps, remember, we see the affected app, okay? In the first scenario, Microsoft Azure was accessed from unusual location, and the severity was medium. Timestamp, of course, is important to document. In the next alert, impossible travel activity affected 2 applications, okay? And it was medium, and that's the timestamp. So what happens here, the Microsoft Cloud app detected 2 logins for the same user from geographically distant locations within a time frame, as you can see, that makes normal travel impossible. 2 minutes difference here. That's what we call impossible travel activity. So login from Netherlands, okay, and then login from another country minutes later. See the connection between these 2 timestamps? 2 minutes difference. Impossible travel between 2 different countries. So here, Microsoft Defender for Cloud Apps calculates whether the user could realistically travel that distance. In SOC terms, this is an indicator of either session hijacking or stolen cookies, or compromised account via VPN or Tor. This is one of the most important identity alerts in the cloud. And here we're talking specifically Azure in Azure cloud environment. Let's talk about now the third alert we have here. System alert, network requirements update for API connectors. The severity is, wow, high. You see, these are system-generated alerts, okay? They do not affect users, they affect systems. So here, basically, Microsoft is notifying the administrators, okay? Not SOC teams, it's for administrators. That API connectors here used for integrating SaaS applications. For us, SOC teams, if we ignore this, Microsoft Cloud Apps Security may lose visibility into connected applications like SaaS, Salesforce, G Suite, and so on. So with the loss of visibility on these, we have blind spots for, threat detection. So these should be treated and not ignored, okay, guys? So these are sample alerts you could see in your Microsoft Cloud App Security. All right, so in GuardDuty, this is a screenshot how GuardDuty looks like in AWS. So basically, remember that GuardDuty is a cloud service that monitors and processes logs in your AWS and issues alerts when there is something abnormal. So when you open the GuardDuty, we see here all the alerts, all the findings that may be of interest for us. So here you can see that the classification, critical, high, low, and medium. If you want to see all the alerts, you can click on findings. And then after clicking on findings, as you can see, guys, we get a list of all the alerts that we have. We have around 10 findings, and they're all sorted by severity. As you can see, we have critical, severity event, and the description says potential data compromise of one or more S3 buckets involving a sequence of actions associated with assume role Lambda parser. So basically, this is quite serious. And if you want more details on this, you can basically click on that, and then you will be able to see the details, such as the MITRE entity and CK tactics and techniques prior to the compromise, of course. That's the finding ID, the type, the region where the compromise happened, and that's the account. And basically, it's important to read through this because in your IR report, you want to write the tactics and techniques involved in the attack. So here we have 4 MITRE tactics observed, exfiltration, impact, discovery, initial access, and 3 MITRE techniques discovered. We have exfiltration, of course, when there is compromise on S3 buckets, you should expect exfiltration, valid accounts compromise, and data manipulation. Now, here are details. We can also scroll more for the details, and we can find in the sections here, endpoints, we can see the actual IP address. This is the attacker's IP address. Endpoints, information about network endpoints that were involved in this attack sequence. This is not the IP address of the bucket itself. This is the IP address of the endpoint accessed the compromised bucket. So now if we head back to the cloud interface, and we want now to take a look at the function that enabled the initial compromise. Remember, we have a file upload vulnerability, and the application was hosted on AWS. So we're going to have it where the Lambda, so in Lambda, we'll be able to see if there are any function names, code created that handles the user input. So I have one function here named file input. Now, what you want to do here, we can also conduct a code review on the function directly. This is the file upload function, and that's the function where the initial compromise started. Okay. So here we have the code source. It's being loaded. So now we can have a look at the source code of this function. You see it is written in Python, and it starts with a function named Lambda handler. And then we can see the access control headers, and then we have try and else, received event, body JSON loads. So basically, judging by these lines of code, we can conclude that this function works on ensuring that the JSON logs are parsed correctly. However, if we continue scrolling down, we can see there is no input validation measure. The weakness in this code lies here. You see we have file data and file name are expected to be sent by the user in the request body. Okay, so we have an if statement here that checks if the file data and file name exist in the request body, meaning if the user is trying to upload data to the web application. This is typical file upload vulnerability, right? Where the user can upload whatever they want. So here it lacks checks on the file data and file name uploaded by the user. And we can see the file data, after it's uploaded, it is converted into or decoded by base64, and the file name, and then attached to the original folder path. The folder path here indicates or equals to uploads. Okay, this is the upload path on the bucket. So basically, the user can upload data to the bucket. Okay, however, there are no checks on what kind of data they can upload. So that's the where the initial compromise happened. So now you know what to do. If you want to investigate whether the attacker actually uploaded sensitive files, malicious files, you're going to have to find the bucket name compliant secure dump storage, because that was the exposed bucket to the public, and where it's actually exposed for a purpose. It's a file upload application. You upload your files and to the application, and that's it. You want to see here if the bucket received any malicious uploads. So we're going to head over to S3. And from here, we can see all of the buckets we have. We're interested in, let's see here, this one, compliant secure store dump storage. Here we can see all of the buckets uploaded. And that's your job now, is to look for any suspicious files. Usually suspicious files they have weird extensions, or they could have regular extension but malicious contents. We're going to look at the CloudWatch logs. Specifically, we want to see how the attacker was able to upload the malicious files. Okay, what API call was used. We want to construct a full URL here. So we're gonna head over to CloudWatch, and from here we're gonna search for the logs. So we're gonna click on view logs, and from here we can basically select the logs. So we have one logs group. Gonna click on this, and from then we can start executing queries if we click on View in Log Insights. However, since our task is simple, we're gonna click on Search All Log Streams and look for the attacker's IP address in the logs. The attacker's IP address, remember, was viewed in GuardDuty. It is 41, 46, 53, 241. So let's hope I can memorize this. 41, 46, 53, 141. Let's see if I'm correct. 241. So you're gonna have to fix this. 241. Okay, we got some hits here. So we have an event, received event. The resource is developer upload, which is basically, it matches the path where the bucket upload path exists on the bucket. And here we can see the headers. That's what we're looking for here. We want to see the API call, the exact URL. That's the exact URL the attacker used, or one of the URLs API that represent the API calls the attacker used to upload the path, to upload the file. And here, let's see. Also, we have other matches. And also, if you look at the host field, we see it matches the first URL we saw earlier. And this header, or this host, was sent as part of a request to dev upload. So maybe we can do this. /dev/upload. Now we have the full exact URL path the attacker used, okay, to upload the bucket. However, this is only the API call. The exact full URL will be the API call, okay, and then this will be followed by the path, which is dev upload. Let's search for this now, just optional, by the way. There was an error. Yeah, we can't use slashes, that's right. All right, so let's get back to the this. Okay, so again, back to this. This is the full URL, the full API call, and that's the URL. Okay, the next thing we want to do here is to look at if there is any identities the attacker abused after they compromised the buckets. All right, let's have a look at this scenario. In this scenario, we have a developer who works in the same organization. Okay, they attempted to steal a secret code, actually could be a program's code that is stored in one of our cloud storage buckets. Okay, so basically how they did that, they did it through impersonating an account identity. Okay, usually account identity impersonation happens through several methods. One of them is generating an access token. So once the attacker or the developer is able to impersonate one of the available accounts that has access to the storage bucket, they will be able to bypass any restrictions that are imposed on their account. So if their account cannot access the cloud storage bucket, now with the account impersonation, they will be able to access the storage bucket and retrieve the files, retrieve whatever there is in the bucket. Okay, so what we're going to do is we're going to analyze the JSON logs, the cloud logs. We talked a lot about cloud logs. We're going to analyze the JSON logs, and we're going to focus on the proto payload array here. Okay, this is the array that we talked about earlier. It's important because it holds all the substantial information we need to look at. Basically, we're going to extract what is the identity that's compromised, what is the identity that the attacker compromised or impersonated, the project scope and the project name, and all necessary information that will help us secure the compromised identity and, of course, remove any infection from the storage bucket. All right, so as a SOC analyst investigating cloud breaches, you're going to first start with, as we mentioned earlier, a scenario where we're given a cloud audit logs. So here we have cloud audit logs for Google Cloud Platform. This log file represents, as we mentioned in the scenario, a compromised project where the identity of the owner of the project was compromised. So we want to find out what happened. The identity was compromised, the caller IP address, user agents, and also if there are any chances if the storage buckets were compromised. So we're given this JSON file or JSON formatted log file. To work with JSON formatted log file, we're going to use a tool named JQ. Okay, so JQ works on parsing JSON formatted log files. So to understand we're going to have to understand the nature of the file. So we can use a simple command like cat Google Cloud compromise.json. Now we want to find out, we're going to scroll to the top and understand the structure of the file. You see, this indicates that here we have a top level array. And under the array, we have a lot of objects, right? So we have proto payload. Inside the proto payload, we have fields such as type, status, authentication information. And also inside authentication information, we have another object such as principal email. And also we have service account name. So we can call this as a file with top-level array indicated by the simple and nested objects and fields, okay? So to call or to reference these fields and extract the values, we can have first to take into consideration that the file has top-level array. So we can reference this top-level array in all our subsequent JQ commands. And then after we reference the top-level array, we can mention the field names such as proto payload, type, status, and so on. All right, so now if we try using JQ and we reference the top-level array, and we then mention the file name, we should get an output that's exactly the same as the output we got when we executed the cat command. You see now that the output is actually prettified. And now you can see, guys, we start with all the fields and objects that are part or included within the main or the top-level array. Now, we're going to explain more how to use JQ with the upcoming and subsequent cloud breaches scenarios. Okay, don't get overwhelmed now how to use JQ. You can follow up on the usage of JQ as we progress further with the cloud breaches or the scenarios. Okay. So now we access the top-level array here, and we see the fields, the objects, and their values. All right. We can see we have a lot of lines, and it's overwhelming actually to go through every single line of them. Okay. So we have to circle back to the methodology. We want to find out first the project name to which the cloud audit log belongs to. At the end, cloud resources consists of projects, right? So we want to find out the project name or the project ID that was compromised and from which the cloud audit logs were extracted. So to find this out, we have two methods. First, we can use a grep, and you can use a keyword such as a project. This will reference, or this will give you all the matches where the keyword project is mentioned. As you can see, we have a lot of relevant matches and non-relevant matches. Non-relevant matches are these project numbers, projects. These are not relevant, right? They do not expose or give out the project name. If we scroll down, we can see this one, project_ID field, and the value is crypto startup. And we also have the name. This is the URL. If you take this URL, it will take you directly to the GUI interface of the project, and we can see the log name. So we have the project ID. But is there another way to find the project ID using JQ only without using grep? So we can go back, and here, again, we're going to execute this command and go back to the top. So here we have main field proto payload, and under this field we have a lot of objects such as type, status, also have authentication information. So probably here we're going to have to use these field names to then catch up to the project ID. Project ID is somewhere here, but we have to use JQ to find it, right? So we're going to clear and use this time, we're going to reference the main field name. We're interested in proto payload. So this will give you all the subfields and objects under proto payload. You see, we have this, starts with type, status, authentication information. And we have request metadata, service name, method name, authorization. Still, it's a lot of data to go through. So now, if you try with the grep project, maybe _ID, you won't find it. Basically, because project _ID lives entirely under a different field, right? It's not under proto payload. To overcome this obstacle, we're going to now print all the main keys inside the main top-level array. So you can do that using JQ. Again, we're going to reference the top-level array, okay? And then that's not all. We're going to use pipe and use the keys function. The keys function allows us to list all the main fields inside the top-level array. So we can reference them and find out all the relevant objects inside each single one of them. And then again, another one, pipe, and then we include the single code, and then sort, or mention the file name first, and output this to sort -u, because we want to sort them and remove all the duplicates. As you can see now, we have all the main fields names: insert ID, log name, proto payload, receive timestamp. We saw earlier that the project ID field was not found inside the proto payload field. So now, right now, it becomes easier to look for the project ID that was compromised in one of these fields. So now the next thing is to reference the desired field by using JQ. Again, referencing the top-level array dot, followed by the main or the name of the main field. Let's start with insert ID, just for demonstration purposes. And then followed by the name of the log file. So inside insert ID, we have these values. This is it. If we try to use log name, and we have these values. These are actual URLs to the project. And actually, you can spot the project name from here, Crypto Startup, just by looking at the URL. You do not have to find the project name by following the field that represents the project name. You can also use, let's try with the resource. Inside the resource field, we have these objects. So type, labels, the bucket name. This is also the bucket, also another one, but they all look the same actually. You see, the bucket name is important bucket, right? And the project ID is Crypto Startup. This one here is the project ID Crypto Startup, and the bucket name is important bucket. You see now we found the project ID just by looking at the relevant or the appropriate field. So right now we know that the project ID that was compromised is Crypto Startup, and the bucket name that was probably accessed and maybe even exfiltrated. We don't have evidence of exfiltration yet, but right now we know that this bucket was accessed, or maybe even enumerated. You're gonna find this out later. Scrolling down, we have audited resource, and this shows the service that was used. Again, we have audited resource, and that was it. That was everything that is connected to the resource main field. But what we got from here is the bucket that was accessed, the name of the bucket, and the project name, the project that was actually compromised. The next piece of information during a cloud breach investigation is to find out the identity that was compromised, right? We mentioned earlier the importance of investigating identities in cloud environments, because identities are the first step or the first initial attack vector that attackers use as a foothold. We're gonna clear right now, and we seek answers about the identity that was compromised starting from this audit log file. Let's go back now to the main fields. Insert ID, log name, proto payload, receive timestamp, resource, security, and timestamp. So where could the identity or the email of the owner of the identity be found here among these fields? Well, we don't know. That's why we're gonna have to first maybe use grep first. So going back to the main array and use grep and use maybe authentication keyword. So we have a field name authentication info, but it's not mentioned here because this object is part of one of these main fields. Now, if we circle back to the main command, and here we mention, or we use, again, try with proto payload, and we're going to grep authentication, and indeed authentication information is found within the main proto payload field. So right now we're going to just remove the grep and print all the objects found inside the proto payload field. Scrolling to the top. So inside the proto payload we have authentication info, as we saw earlier. And indeed inside authentication information we can find the principal email. This represents the identity, okay, and the service account key name. These information are of utmost importance when investigating cloud breaches because it allows you to spot the identity that attackers use to get access to your cloud environment. In our example here is cloud storage helper at crypto.im G service account was used to access your project, and of course later on subsequently the cloud buckets. And here we can see also we have another field, request the data. Inside it we can see object names such as caller IP and caller supply user agents. So this is probably, we're not sure yet, this is the IP address the attacker used, or maybe the machine IP address that the attacker used to perform this attack. And of course we have the user agent. Scrolling down, you can see the service name, method name, other fields as well. So for now we got the email address, or the cloud identity, in other words. So now, having known that this is the field that stores the cloud identity, we're gonna copy this and go back. Okay, remember we're referencing the proto payload field because it contains the authentication information, and we're gonna now grep. It becomes logical now to use grep followed by the field name, which is principal email. You see now we can see all the email addresses or the cloud identities within this project. As you can see, the identity is the same across all values. It's cloud storage helper crypto startup. So right now we are sure what was the compromised cloud identity within this project. Now let's go back to the IP address. What was the IP address the attacker used to access the buckets and this project? So basically, again, proto-payload contains all the relevant artifacts. So we're gonna now go back up. You see we have a field name, caller IP. It was here. So we're gonna copy this. And here we're gonna use grep caller IP to see all the IP addresses that were referenced in this file. You see all the IP addresses point to the same value. Of course, this is within the proto-payload field. However, if you want to access all the field values using the main array or the top level array, you can just do that as well. And you can see all the IP addresses as well. So here it's the same. This is the IP address of the attacker. You can use geolookup services now to look up the country where the attack or the attacker from where the attacker launched the attack. All right, now let's talk about user agents. Another piece of information or artifacts you want to find is the user agent, because it's part of the IOCs or indicator of compromise. Up until this moment, you got the IP address, you got the cloud identity email. Now you're looking for the user agent because it gives you the device information, right? So going back here, we're gonna use grep just for exploration, grep user. And we have a field named caller supplied user agent. We have caller, only this one, caller supplied user agent. And we have a lot of values. You see here we have API tools Python 3.11.3, and this is the same across all these values. And we have another set of values that are also the same. Google Cloud SDK, gcloud 390, 00 command, gcloud. All right, so now we're gonna, again, go back to the main fields and remind ourselves of the name of the fields. Insert ID, log name. We saw that proto-payload holds most of the artifacts. So we're gonna go back to proto-payload and look at the supplied user agent. You see, guys, that the IP address we saw earlier associated with the attack, okay, is actually mentioned along with the caller supplied user agent that points to the user agent equals to the Google Cloud SDK, not the Python one. So that's the user agent of the attacker, not the Python user agent we saw earlier, because it is linked, or we can correlate it with the IP address we saw earlier that is associated with the attack. All right, now talking about timestamps. Going back here to the main, so right now we're printing the top level array, and now we're gonna grep for timestamp. With a lot of timestamps, you can see the first time the project was accessed indicates this value, 2023-07-27 July 2023. And that's the exact timestamp, but we do not know yet what this timestamp represents. Does it represent a failed attempt, a successful attempt to access the bucket or the project or another service? We just don't know yet. So right now we're gonna go back to the keys, and we have received timestamp and we have timestamp fields. Let's print out all the objects and the values within timestamp field. So here, again, we print the top level array followed by the timestamp. Gonna remove this and have a look. So we have all these timestamps and exactly the one we're looking for, this one. However, we want to find more context about this timestamp. Maybe we can find this under receive timestamp. And we find the same values. Okay, let's go back to the main command and use resource field. And here we're gonna grep for timestamp. We don't have. Let's go back to proto-payload. And also we don't have timestamp information inside proto-payload. All right, now let's go back to the main fields one more time. So right now we want to look for the bucket name that was accessed. We already know that, but we want to know if there is any file exfiltrated from this bucket and what tool or command line tool was used and what API was used to exfiltrate this file. At the end, we want to find out the extent of this cloud breach by identifying the files that were exfiltrated from this bucket. Recall now that the bucket name that was accessed was, let's go back to the a main command, and then we use the proto payload field, proto payload. Maybe we can use grep bucket. Okay, so this is the main resource that was accessed. Projects, buckets, important bucket, that's the bucket name. And the resource that was accessed or the file is secretcode.java. That is your file that was accessed by the attacker. Was this file exfiltrated? And what tool was used? What API method was used to get this file? That's the answer we want to find. So to do that, we're going to go back and have more context about these exfiltration attempts. Scrolling till all the way up. Remember, we're not going to go over the file or over the output. We just want to find out the fields. Okay, so you see the caller IP address here is the same. The caller supply user agent is API tools Python. We still want to find out what does this mean, because here there is the usage of this tool, which is GS utility, a command line tool provided by Google. And here you can see the caller IP to use this tool. And this is the timestamp. You can find more context as we investigate more about this activity. But we want to find out information relevant to the buckets. You see, we have authorization info. Okay, lists all the information or the objects related to the bucket access. Also, you have method name and service name. So that's the method name or the field that represents the method name or the API that was used to access the object, which is the bucket here. So if we use this field name in our command, going back, and then we grep, maybe even you can use it here. Dot. So we get all the API calls used here. We have storage objects get, list, and we have buckets.list, and we have service usage to enable service. We're going to ignore these. That's what matters now. Storage objects get and storage objects list. Okay, so this means that the attacker used the objects list API to list the buckets and use objects.get to retrieve the contents of the buckets, namely the file we saw earlier. So if we go back up, you see across all the methods used, that's the method name. And inside it, we can see the authorization information. So if we go back and use authorization information here, and we get all the access attempts. So here we have an API call to get this object. Remember, get is to download the object or to retrieve it somehow. So this is the file that was used or retrieved, secret code.java. Probably this is the file that the attacker has exfiltrated. Here we can see the API call objects.list to list the buckets available. We have important bucket, that's the bucket that was accessed. And we can see information about the permission. Since the identity that was used has access to the buckets available in this project, of course, the attacker will be able to access these buckets and the permission will be, or will allow it. So right now we have pieced together all the information about this attack, the IP address, the buckets was accessed, the file that was exfiltrated, the user agent, the identity was compromised, just by looking at, or just by parsing the cloud audit logs file we were given and using JQ. In this scenario, we're going to use Microsoft Sentinel to analyze the cloud logs and extract the indicators of compromise in Azure environment. So here, the SOC team has noticed suspicious activity in authentication logs. They think that there might be someone who has hacked into one of their cloud accounts and is actively using this cloud identity to compromise or to sneak peek into the existing infrastructure. So we have to find out and spot this suspicious pattern. So basically, therefore, we're going to look into the authentication logs and we're going to use the log analytics to extract the indicators of compromise. Once we extract the indicators of compromise, we're going to create analytics rules that will trigger alerts when there is an activity that is similar to the spotted suspicious pattern. If we do that, we'll be able to receive alerts and we'll be able to make the cloud environment more secure. Okay. Additionally, we will learn how to enable various policies, security policies in Azure environment. Let's get to it. All right, guys. So here we are at Microsoft Sentinel, and we're going to now start analyzing the sign-in logs. We explained the sign-in logs in the previous sections. Now it's time to use Microsoft Sentinel to analyze your logs. Okay. So basically, what we're going to have to do first, we're going need to click on logs from here. I know you're familiar with this, but just a reminder. And then we're going to need to spawn the logs that we have. So we're going to click on the tables. And from here, my logs are sign-in logs. You see, I'm going to run the query run to retrieve all the logs ingested into Microsoft Sentinel. You see now, that's the query here. Of course, you can select KQL mode, or you can just select simple mode so that the query runs in the background. Failed to resolve a type expression named. Okay, if there's an error, we're going to have to get back to KQL and see what's what. So here we have sign-in logs. Okay, execute. All right, so now we have retrieved logs, retrieved all the logs we have. And basically, we're gonna have to drag this a little bit up to get ourselves familiar with the columns. Of course, you can click on the chart to have a graphical representation of the data, but this chart will work perfect when you have a query here to retrieve specific type of data. Okay. So as you can see, we have the time generated, the timestamp of the event, the resource, the tenant, and the operation name. You see all the logs indicate that they are sign-in activity. Category sign-in logs. We're just focusing on sign-in log because in our scenario, we have a password spray attack taking place. We're going to have to find out what is the attacker IP, when it happened, and what are the affected users, and so on. All right. So what we're going to have to do first is we have to look at the pattern. You see, guys, we have in the result description, we got a lot of invalid username and password. In the result signature, it indicates failure. And you see the result type equals to 50126. So basically, these are critical information to note because we're going to need to use them in the query to be able to filter and narrow down the outcomes. Also, you can see, guys, we have the location, and it's denoted by the region where the attempts, I'm going to say the attack attempts, are coming from. Of course, you can see also the username and the application where the username is connected to. And of course, the IP address. All right. So the first thing we want to do here, we want to find out, how many failed attempts do we have? We see a lot of invalid attempts to sign in. Since password spray attacks target all user accounts in your tenancy with a single password, first we're going to have to find out how many failed login attempts do we have. And from there, we're going to narrow down more. So we keep the sign-in logs here, the index, just like Splunk. And then we're going to use pipe time where time generated. So here, the time generated has to be equal more than 24 hours, just to be on the safe side. Of course, that depends on where you have ingested your logs and depends on the pattern observed here. You see, most of the logs here indicate the current today's date, which is, as you can see, 10 December. So to be on the safe side, I want to ingest all the logs at around the last 24 hours. Okay, so we're going to use ago, and with 2 parentheses, we're going to use 24 hours. Okay. In the next query here, I want to only retrieve the logs where there are invalid attempts or failed sign-in attempts. So basically, I'm going to have to look at the result type here. You see, when the result type equals to a specific value, not equal to 0, it means this is a failed attempt. When there is a successful attempt to log in, the result type will be 0. So maybe first you may be tempted first to find out what are the successful attempts to check out if the attacker was successful in logging in. To do that, we're going to have to use, again, where, and result type has to equal 0. Okay. So once we do that, we'll be able to see all successful sign-in attempts. But again, this is not a good indicator that the attacker was able to sign in because it could be a regular user, right? But it doesn't harm just to take a look. And then we can use project because we're going to see to select the columns we want to display here in the logs. So we're going to opt for the time generated, display time generated. And I want to see also the user ID. So we're going to type user principal name. Okay. And then let's see if we can retrieve also the IP address. You see all the fields automatically pop up from here. You can select them. Just type the first 2 hints. And I want to see the application, of course. So we're going to select from here application display name. And then the result type, of course. and I want a description. The description helps you to see the description of the sign-in attempt. Okay, more information, invalid, sign, success, what so on. And then we can use order statement. Okay, because remember in forensic investigations, you want to be mindful of the time. So we're gonna reorder or order the events using a descending order from the very latest to the earliest. Okay, our query now supposed to be fine. No query was selected. So we have two successful sign-in attempts. As you can see, guys, the username is Louisa Hartis. That's the IP address, and that's the application name she logged into. It's Azure Active Directory PowerShell. This could be the compromised identity, and it also could be just a regular user signing in. We can't prove it yet. What we can do here is to take a note of the IP address. So we can copy this value. And here I'm going to use Notepad. And here I'm going to type successful sign in IP, and I'm going to take a look at the user, copy the username. Because remember, in SOC investigations, you want to correlate your data. So we may need to correlate this data later, and that's the username. I'm going to keep this here and continue with the investigation. So you're going to get back, keep this as is, keep this as is, just change this. We want to look for failed attempts. So instead of the result type equals to 0, we're going to have to make it not equal to 0. Okay, and we have a look. So all of these are failed login attempts. We can verify that our query has successfully retrieved the results by looking at the result description. You see here all the results show invalid username or password, or invalid on-premise username or password, which means our query was successful. We have additional queries here. Account is locked because user tried to sign in too many times with incorrect user ID or password. That's the IP address. If you look at the notes here, you see the IP is similar, but here the failed one ends with 150 and it shows different user. Now that could be the attacker trying to sign in, okay, to multiple accounts with the same password. Okay, the password did not work on the user account. However, it may have worked on this user. I'm just here assuming, okay, because we have a lot of invalid attempts. This is a red flag. Also, we have account locked because user tried to sign in, and the account is Jonas, also Guerrero, Davis, and Frederick. Okay, so these locked out attempts also worth investigation. Now, here it's worth mentioning, guys, that you see all of the result type, the value doesn't equal to 0. Okay, this is a classic indicator of failed sign-in attempts. Now, what we're going to have to do next, I'm going to have to start correlating the data. So we need to find out more clues about these invalid attempts. What is the common denominator between them? So the only thing to find here or to look for is the IP address. We want to see the IP addresses which have the most failed login attempts. This gives us, okay, an analytical indicator where to look later. Okay, so let's have a look again at our query. So we're going to keep this as is. The logs generated in the last 24 hours, that's fine. The result type has to be not equal to 0, that's fine. And then we're going to have to do some statistical magic here. We're going to use 5 and then use summarize failed sign-ins, let's say without the dash, okay? And then that's the variable we're going to define. This is the variable that will hold the count of the failed sign-ins. But how we're going to group them? We're going to group them by the IP address, okay? So we're going to say equal to count, which is also a statistical function you can use in Sentinel to count the number of occurrences of a specific field. Here we're looking at the IP address. So basically we're going to use count by IP address. Okay, we're gonna keep this. It's fine. We're gonna keep this as is. And order by. The order by it has to be ordered by failed sign-ins in a descending order. And lastly, you can limit the number of results by using take. Okay, in Splunk you use limit. This is not Splunk. Here we use take. Let's say take 20. Let's see. Project operator failed to resolve. Yeah, looks like we're gonna have to remove this because since we are using statistical functions and we are using ordered by, the outcome here will be just the columns indicating the value of the failed sign-ins. You're gonna have to remove this and see if this works, and it worked. So we see, guys, the IP address which has the most failed sign-in is this IP address, 15.9. Also, there is an additional one, 14.62, and the rest, it could be actually a network of IP addresses from which the attacker is trying to sign in. It could be all of these IP addresses belonging to the attacker, but in log analysis and cloud investigation, what matters most is the one which has the highest suspicious attempts. So we're going to focus our investigation on this IP address here. Okay, so the next thing to do here is to try to query or filter our query here based on only this IP address. So we're going to copy this and get back here. So next thing we want to do, we want to find out what are the users the IP address here has targeted. So we're going to get back to the query here. So this is going to stay the same, and this is going to stay the same. We're going to cancel the summarize. We're going to cancel the order by. We're going to cancel take 20 for now. And here we're going to say where IP address equal to this value. And then we're going to use project. So here, use user principal name, result type, of course. Result type, result description, and you want to use order by descending. Let's see here. Okay. Looks like we have forgotten to put the time generated here. So order by time descending. Failed to resolve scalar expression. Let me see here. Looks like we have two conflicting queries. Where and ordered by. Why are we using ordered by? I don't know. So I'm gonna cancel this. All right. So this IP address has targeted these users: Marisol, Frederick, and all the result type indicate failed attempts, which means that's good news because it means the attacker was not able to successfully sign in to the targeted accounts. It means there was an active password spray attack, but fortunately for us, it wasn't successful. However, you want now to get back to the previous query, right? And correlate the list of IP addresses with the IP address here that has a success sign-in event. If one of these IP addresses match this one, it means we have been compromised. If there is no match, it means we are in the safe side. So what we're gonna have to do next here, let's get back to the query. Keep time generated, keep result type. Just we're gonna have to use again, summarize, failed. Let's keep it failed, keep it short, count by IP. And then I'm going to order by failed, descending, and then gonna remove these and say take 20. Okay, so all of these IP addresses you see, they are similar to each other, and none of them equal to this one. Now, that is actually something that you can rely on, methodology that can rely on while investigating password spray attacks. However, if you want to further verify your theory, you want to copy this IP address, which is associated with the successful sign-in, and you can find out if this IP address was spotted in previous failed attempts. You're gonna have to copy this IP here, get back here and say where IP address equals to this value. Just this. Okay. We have one failed attempt, only one. Let's have a look. Why? So the result description due to a configuration change made by your administrator or because you move to a new location, you must enroll in multi-MFA to access the tenant. All right, that is a description of why the attempt was a failure, not because it is invalid as a name or password, right? You see all the other fields look just fine. Most importantly here, we looked at the result type. Yeah, it indicates a failure in signing in. However, the description doesn't say invalid username, which means that the user correctly signed in from the first time. But due to the configuration change that has been imposed by the admin to enforce MFA, the user was not able to sign in, and they need to enable MFA in order to get back to their account. So that looks healthy here, which means that the attacker, we can safely assume that the attacker was not able to compromise our Azure tenant. Okay, now we finished the detection phase. Let's now see how we can respond to such incidents. So we can use the Content Hub. You will say unsafe edits, okay. And from here, we can look for the Entra ID. So basically, we can use this one, Microsoft Entra ID. This will enable us to create policies to respond to sign-in events. So we're gonna click on this, and then we're gonna install. Next, I'm going to click on Analytics. And from here, let's look for, these are the active rules we have. Okay, let's click on rule templates. And we want to create a rule to detect password spray attacks, multiple failed login attempts against multiple accounts. You can search for spray, and we have, as you can see, 3 rules. This one is password spray attack against ADF sign-in logs. We want the one that handles the applications or the failed attempts against applications. This one, password spray attack against Microsoft Entra ID seamless single sign-on, not this one. Password spray attack against Microsoft Entra ID application. This is the one you see. Identifies evidence of password spray activity against Microsoft Entra ID applications by looking for failures from multiple accounts from the same IP address within a time window. If the number of accounts breaches the threshold just once, all failures from the IP address within the time range are brought into the result. Let's create this rule and configure it to use the logs. The severity, you can put this as medium. These are the MITRE techniques: credential access and brute force. Okay. The rule query, anytime details. This is the query that will be launched. Okay. All right. Now configuring the query. Since we want the rule to be applied to the logs we have analyzed, we're going to have to take a look at what is the variable used to refer to the logs that will be monitored. So we scroll down, we see here there is a reference for a variable name, table name. However, the table name is not defined. So if we leave this query as is, it will not work. So we're gonna have to define a table name. What is the table we're gonna apply the rule to? So we're gonna copy this and use let table name equal sign in logs. Don't forget the semicolon. All right, so now let's look at alert enhancement, entity mapping. So the IP address here will be mapped to, address is mapped to IP address. Let's have a look. We can also map other entities here. For example, we're looking for the account. The principal name has to be, so here is the mapping from the query into the queries in the logs. So here in the logs, you can look for user principal names or display names, and we can use here full name. Okay, we can also add a new entity and look for the Azure resource. Here it is resource ID, and here we're gonna use the targeted application. Additionally here, of course, there is no URL. We're gonna look for other fields that may be of value. So that is enough for now. Custom details, here you can surface particular event. All right, alert details. Next, query scheduling. Run query every day. You can configure this to run every minute, every hour. That depends on your environment. So I'm gonna leave this as running every day. Look up data from the last 7 days. We want to see, that's fine for this scenario. Start running now automatically. You can configure also a specific time for the alert, or the alert schedule rule to run, so that it produces alerts after the specific time window is set. But for me, I'm gonna leave this automatically so that the rule runs now. Alert threshold, generate alert when number of query results. All right, so let's go up here before we define what should be this value. Table name, time range, look back, authentication window, 20 minutes, authentication threshold. So here, I'm gonna have to change this value to match the scenario we have analyzed. Remember, in the scenario analyzed, the failed attempts were a maximum of 6 for the most used IP address, and others had 4. So we want the rule to trigger an alert, right, before the attacker reaches this level of failed attempts, like 4 attempts or 6 attempts, because if we leave the attacker trying more than 4 or 5 or 6 times to sign in, probably at one point they will succeed, okay, with the right password or the right account. So we want to cut the way on the attacker, and we set a value threshold just below the documented values we have seen. So we have seen a maximum of 6 and 4. You're going to set this to 3. And failure codes, success codes. Okay. Generate alert when number of query results is greater than 0. Okay. Group, event grouping and suppression. Next. Now here we configure how the instance is created. So basically, when the rule triggers an alert, we should check it out in the incidents. So here it creates incidents from alerts triggered by this analytics rule. Yes, create an incident, because we want to find out, we want to be alerted on this. Alert grouping, we're gonna just check this. Now, if you want to create an automated response, you can configure it here, but for now, we just want to be alerted. Review and create, and then save. So now the rule has been saved. Whenever there is more than 3 failed attempts against at least one of the accounts, we will receive an alert. All right, guys, our next scenario is using Splunk SIEM to investigate a breach to AWS environment. So the breach happened to one of the identity users. Okay, the CloudTrail logs have been ingested into Splunk for you to start the investigation. And we believe that the identity and access management compromised identity was used to, of course, manipulate and get access to the buckets and change some configuration in the AWS environment, probably creating users for persistence. So what we're going to do in the lab scenario here, we're going to use Splunk to investigate the CloudTrail logs. That's a perfect scenario when establishing your SOC environment. You want to ingest all the logs, CloudTrail, maybe even GCP and Azure, into one central SIEM. That's a perfect scenario, perfect environment to analyze cloud incidents. You don't want to hop between logs, use JQ every time. Still, JQ is valuable, but you still want one central place, user-friendly, to analyze the logs. Because let's be real here, I don't like to use JQ every time to analyze logs. Okay, Splunk, Elastic is actually perfect, or maybe even IBM QRadar also is perfect for these kind of things. So let's start now. We're not gonna extend a lot of theory. We're gonna start the investigation right away. Okay, so our analysis in Splunk here starts with retrieving the index. Remember, we're retrieving CloudTrail logs from AWS, and that's the perfect way to analyze logs from multiple sources, such as, of course, in the cloud. Pull them into SIEM and start the analysis from one central interface. All right, so here, after retrieving the logs, we want now to focus on, again, the failed login attempts. It's the typical way of uncovering what was the compromised accounts. On the left, we can see the fields. Basically, we are interested in the event source. We want to pull all the events, all the authentication events and sign-in events. So we're going to have to look for the source. If we don't find it, we can click on more fields and look for source and click on event source, and it will be added to the list. It wasn't. Okay. Have a look at the event source. You see here, we're going to select the sign-in logs. That's what we're interested in, right? Going to click on this. And we have around 35 sign-in logs. Okay. Next filter is finding out the failed ones, the failed login attempts. How do we do that? We can have to see if we can filter by the error message. So see here we have one error message in the field. Error message. We have around 19 events failed authentication. Total number is 35. So if we can click on failed authentication here, we will filter and narrow down our query a little bit more. And we have around 19 fields, all failed authentication. Great. Now we want to see the user, okay, that was subject, for the users that were subject to failed authentication, meaning those were the users who were attacked. Okay, so we're gonna now use stats count by the username field. So here the username field is user identity key access, user identity username, this one. Okay, so we're gonna, okay, so we can write this user identity username. All right, so doing that, you can see the count of the usernames. What we want to see the sorted version of this. We can use sort dash count. And now we can see, yeah. So help disk look has the highest number of failed attempts, 10 failed attempts. That's abnormal. Remember in the Azure Sentinel scenario, we suggested a good rule of thumb that after 3 failed attempts, we raise suspicions. Now here, most of the users, all the remaining users have not more than 3 failed attempts. So now the attention should be redirected to analyze help disk look. Can I click on 10 and see the events? We want to find out if these failed attempts are followed by one successful attempt. All right, so this is descending order. Scrolling down, as you can see, guys, analyze the events. And here you can see the error message indicates failed authentication. That's one failed authentication. That's another one. That's another one. All the way up to the last event, you see the error message has, you see also there is one here, failed authentication. All right, so I want now to focus on this user, which is help disk look. Okay, I'm gonna now remove the error message here because I want to see if there was a successful attempt. So filter now and see if there's any successful attempt, and we have, looks like we have successful attempts. All right, scrolling down, you see here, there is one failed authentication, okay, and then the error code disappeared, or the error message disappeared. So the first successful sign-in attempt was at this time. This is your timestamp where the first compromise happened. That's the source address, and it should be consistent with the IP addresses seen earlier. Source address here is the same, right? So that's also the source IP address of the attacker. So after the attacker has signed in, now it's time to pull all the actions the attacker took. So we're gonna cancel the event source. Right now we know what happened in the sign-in logs. We want now to find out more about the activity of this user that was compromised. So let's see how many event sources going to be pulled when we filter for this username. Scrolling down, event source disappeared again. Host, source type. Event source. So we see we have 186 events coming from the buckets. And then we have 179 events for the identity and access management. Let's now focus on the buckets, see why there is high volume of event calls to the buckets. All right, so now we're gonna see the event names. What are the events? By clicking on the event name, we see get bucket public access block. And we have 23 events. Again, get storage lens configuration, get storage lens, get bucket ACL. So it looks like the attacker was enumerating the buckets. Remember that these are the top 10 values. It doesn't mean that these are all the actions the attacker took on the buckets. Okay, so what we can do here, we can scroll up and say table, time, and then event name. Okay, want to see all the actions the attacker took on the buckets, sorted by time. All right, so here we see list access points, get bucket ACL. At the end, we want to find out what where the buckets the attacker accessed. It looks like we have a lot of events. So we're going to use DDUP event name. Okay, you see you have list buckets, and then we have get object. So it looks like here the attacker tried to retrieve some file from one of the buckets. Now, if we want to find out what was the bucket from which the attacker retrieved the file, we have to focus on this event from here. So we can go back, and now we want to find out the event name equal to get object. Okay, let's see how many events we have. We have 8 events. Now let's do some sort by time. Okay, we're going to put the event name. And then we want to see the bucket name. How do you find the bucket name? We're going to focus on the request parameters. Remember when we talked about AWS logs, we mentioned that under request parameters, you will find all the details about the event or the details of the API call that was accessed. Here, the buckets. So you see response elements, source IP address, and we want to look for bucket name as part of the request parameters. So here we can find it from here, request parameters host key bucket name, this field. Okay, so now we can use this in the table. So request parameters bucket name. Okay, and let's see if there is anything else we can retrieve, such as maybe what is the key here? The key is the file. Okay, we can request again parameters dot key. So this will give us the bucket name. This will give us the resource that was accessed or retrieved. And we see all the events, get object, and of course they are sorted in an ascending order, not descending order. That's the bucket name, and these were the files retrieved. You see, from this bucket research project files, this file was retrieved prototype.object, and of course we have a backup file. So we have a lot of buckets that have been accessed, and different files were retrieved from these buckets. The next thing you want to see is what are the actions, other actions the attacker took on the bucket. So we're going to get back to this, and we're going to see the event names, the available event names. So here we see get bucket public access block with 23 counts, which means here the attacker was trying to make the bucket publicly accessible, probably to facilitate data retrieval or to leak data to the public. Can click on this and we see what are the affected buckets. So here event name get bucket public access, and that's the source IP. Still, the source IP here is different from the IP the attacker logged from. So here, to make this easier on us, we're gonna use table time and then the bucket name. See what are the buckets that were changed to public access. Marketing assets, Vault, AWS CloudTrail logs, and a lot of other different buckets. But this is a lot of buckets to be public visible. So here, get bucket, looks like we made a simple mistake here. So get bucket public access block is blocking the bucket from becoming public. Making the bucket public is by putting, instead of get public access block, here it's going to be put, not get. So here it's going to be put. And now it makes sense. We have only one bucket, which was changed from internal to public access. This is the bucket name. All right, now let's get back to the same user identity. Now we understand that the attacker compromised this user identity and exfiltrated some data from the buckets and changed the access policy to public. The next thing we want to do is to find out if there was a persistence mechanism implemented by the attacker, because most of the time they do persistence on the compromised environment, because this account is an internal account. At one point, you as a SOC analyst or the response team, they will remediate this account and secure it. So the attacker knows this. Okay, so we're gonna have to get back to the original logs and see if there is any indicators of persistence mechanisms by looking at events that suggest a new user creation. So here we scroll down to event name, 81 events, and these are the top. Okay, what we can do here, we can go up and use table time event name, get the list of all the events, and maybe even dedup, because same event may have been called more than one time. Let's look for indications of any user event, like create user, add user. So list users, get user, still not persistence, looking for create user, add user to group, and create user. That's suspicious. We're going to click on this one and open it in a new tab. This will execute the query with create user here. Just we have to event name not equal to user. Well, we're gonna just modify this and say event name equal to create user. What was the user created? You see one event name create user. That's the event source, identity and access management. That's the IP address. And the username, still, we can't see the username. User agent, user identity. I still can't see username. Response elements, username. The user is marketing.mark. And the user identity, see help desk look. Here, the ARN indicates the user that issued the event call. The event call here is create user. Okay, so help desk look issued the create user event call to create a new user called marketing mark. That's your persistence user. And probably now, if I filtered the events to focus on add user to group, it's going to show that the user that is added to some group is marketing mark, maybe to administrators. Let's find out. And here we have one event. Let's have a look at the details. Scrolling down. Again, help desk look has added or used the event add user to group, and the group is admins and username is marketing mark. So now the full chain has been constructed from the first compromise till the persistence. Okay, so that's your full analysis completed.